here, and it's just a SharePoint, so I can just say like free up space, and it can just clean all the space from here, and I don't
Oh,
have any hassle. And same on the desktop. Anyway, I I preferred it that way.
that's good. That's good.
Yes. See this lightning.
Uh-huh, uh-huh.
So the guy is supposedly there are three signal, right? RTF,
Yes.
RFT, impulse, and phase, right? So if
Yes.
we go inside, they are transmitting these two as well, RTF and
Uh-huh,
this, right? But
uh-huh.
not this impulse. So what I am thinking is not that like this impulse should be A.
No, no, no. Actually, that's one type of modeling. If you want to model anything in the module, like
Yes,
if you create a module
yes,
from one module to another module, if you want to take the data tab or the data signal,
yes.
you have to you use that component. Like we will explain in TRV. Like we will be using that component TRV.
So if I go here, right? So that's
Ah,
RFT is transmitted from here, right? Here
yes, yes,
you will see here.
yes, yes.
Then the same way the phase thing was somewhere. I don't know where that was. Not in this one, but it was in another one. I think the phase one. It was somewhere.
It is in the source. It is in the source actually.
Source,
Source, source.
Oh,
source.
source. Yes, yes.
Not here. The
Source.
left side.
Oh, sorry. Oh, yes,
Yeah.
this source. Yes, sorry. Apologies. Yeah,
Okay.
this one. Yes. So
Yes.
same way, this is a phase, right? And this is a phase transmitting from here. My question is, I can't run it, but how this guy is receiving this, because he is just only controlling that impulse thing, and then here is this as a one of the variable is impulse, right? But to get this in, you need to transmission from same node somewhere, right? If I am not misunderstood. So if they like intentionally put this impulse and then
No,
intentionally
no,
put this in.
no. What he has missed out is like he has missed out this thing. Can you go back this into the surge generator?
Okay, here, yes.
Surge generator, surge
Or,
generator.
or certain,
Lightning.
yeah, lightning one, yes. Yes,
Can you go inside this surge generator?
yes, here, yeah.
No, no, the left side one. Yes.
Or this one.
No, no, not
No.
this one. The right, this
You
one,
mean
this one.
graphic?
No, 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 no. The waveform.
Right.
Yes,
This
that
one.
one.
Yes,
This is called surge generator.
yes,
Okay. Here, can you see this? Here he has given the peak amplitude as 150,
yes, yes,
150 kilohertz. But
yes.
here he should give the signal as impulse.
Yeah. That's
Then
that's
he,
that's yeah. I think these people do, this with the intention, like so that you can ask them back.
okay, okay.
I think so
But
because I realized this in couple of more example as well.
yes, yes. But what they have done is like they have actually disabled the multi-run in this example. That is why they have kept this.
One
Can,
150 ampere, yeah. But you will
yes.
know only these things when you are like so much expert, or you get
Uh-huh.
some like help, external help, like I am getting from you guys.
No, no. These are all some basic things which we can do after doing some basic things in PSCAD.
Yeah, yeah,
That we,
yeah,
yes,
yeah.
yes.
That was one thing. Another thing is, see in this one, this tower has this BRKs, right?
Yes,
All the towers. The
yes.
question is, what this BRK is doing this signal on the footing side. I mean, why it is here? It's not
BRT,
here. It's there. It was kind of confusing to me. So
BRT
so
signals.
so this is a BRK according to them.
Yes, yes.
All the BRK. I don't know what they are trying to do with this, but
Can
here there is nothing like BRK.
no, no. In below, can you see this? There is something
Yeah,
called as breaker signals.
yeah. These breaker signals. Yeah,
These are the breaker signals. Can you
yeah,
go up? Yeah.
yeah.
Can you go up? There they have used some breakers, right? Above.
Oh yeah, yeah, yeah.
These are all the breakers.
Yes,
That
yes,
is why they have given. This is how they have used the breaker signals here.
yes.
Uh,
But
Here they have been.
it was in
Yes.
this schematic to the here for some reason. It's just for showing. I think it's doing nothing here, or is it doing something here?
No, no. That signal, I hope it is in the below. Can you see this? There is something called as breaker
Yeah,
signals
yeah,
below.
yes, yes.
Right side, right side, right side.
You or
Here,
right side?
here,
Or
here.
this one? Yeah, yeah, yeah.
That is the signal which they have been referring there.
Yes.
Outside we can do any kind of modeling, like we have modeled the one and a half breaker scheme, right?
Yes,
One and a
yes.
half breaker scheme we have shown, like we want this kind of output, then we can model it as anything we want
Yeah, yeah.
to show it as an output, so that for their reference they have shown it as an like
I just
output
like
which
that.
they have
Yeah.
shown. Yes,
But
yes, it is.
it's really confusing. It's not really connected to this.
Yes, yes, it is just for information sake. That's
Yes,
it. That's
yes,
it.
yes, 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 yes. Okay. And this is not a module, if I am right. You know, they
Yes,
created this on their
they
own.
have created. If you double click and go for help,
Yeah.
can you go for help?
Nothing comes up.
Here you can see this. There is no anything will be displayed. Nothing will
So
be displayed. So
the question on
it
this
is
is if I run these calculation, for example, right? So can I say copy and can I use this somewhere as well?
yes,
Is that possible?
we can use. But what I have to do is, like, you cannot directly copy this element. What you have to do is, like,
Copy
no,
transfer or
no,
something?
no, not like that. What you have to do is, like, just to go the left side, untitled. There you have projects, master
Oh,
library. Yes, and there you can see plus sign this, and
yes.
then inside go to the
Definition.
definitions.
Yes.
Definitions. Just to wait here on the leader progression model which they have used here. Just to go and wait here. Can you? Yes, just to
This
wait
one?
here. What is the model it is showing? It is
Eh,
lightning example leader prop.
yeah.
It is the
So
name of the
um,
particular block.
yes.
Then what we have to do is, like, we have to
Find that out.
find the leader prop. There it is. There it is. Can you see this? Below that.
This one or leader
No,
prop.
that you right click on that.
Yes.
What you have to do is, like, we have to just double click, not copy this definition onto the clipboard, pasting the definition into a definition list page. Oh, yes, yes. This is somewhat different from the version which we are using now.
Yes,
What the
yes. That's what I
interface is like
realized.
copy definition, right?
Yes.
Here, if we copy this definition, it will be in the clipboard. Okay, just copy this.
Yes.
Okay, and what we can do is, like, if you are opening some other file, just for example, if you are going to open a new file,
Right.
you have opened, right? In
Yes.
this, what we can do is, like, just to do the things which we have done. Not here. Yes,
Yeah.
there. Go right click on the definition. Right click on the definition. Right click on the definition and paste.
Paste is special or
Paste.
paste?
No, just a paste.
Okay. And then it says something is moved here. I need to see where it went.
Definition cannot be pasted. Check edition limits for more information. That
What
is
I was
what we.
thinking is how I can do it. I
Oh,
might be wrong. I copy like that,
no,
right?
no, no, no. That
And
you,
then go
if
here
you do that, if you
and
do that, what happens is,
then
like, the
do
particular.
paste transfer. But even after that, it's not working.
Uh, what it does happens is, like, you are not copying the library completely. That is why it happens like that. What in PSCAD what we have to do is, like, we have to completely select the library file of the particular module, like
Okay.
we have done here. Just right click on that. Not like that. Just to go into the lightning example. Just to
Yes.
go into the lightning example. Just we have did right lightning
Yes.
prop. Just copy with. Yes,
Copy.
copy. Yes, copy and go inside that and
Another example. Yes.
yes, paste with the dependence. Right click on the definition, right click on the definition,
Yeah.
paste with the dependence, paste special, paste with dependence. Yes, now
Yes.
here you can see, right? Now just to no, what you have to do is, like, just right click on that.
Okay.
Mm,
Instant.
create instance. Yes, create instance. Then okay, I hope they have blocked this option in here. That is why it is not coming. I hope. But this is how you have to paste the use the module from
Okay.
different page to this page. Yes.
Oh, someday I will know. Don't worry.
Yes. What you have to do is, like, this the option which we have used is correct. Okay,
Yes.
but what I feel is, like, they might have blocked this option. I hope Or else we can do one thing, just to copy that,
Yeah.
Not like that, in the left side,
What left side?
left side,
Oh,
on
here,
the
sorry, here, guys.
workspace, on the workspace on the
Sorry.
left side, just copy. No, not like that. In the file where we want to paste the model, THNOTL.
Alright,
That's what I'm saying.
here.
Yes.
You
Just
will copy this?
just copy,
Yes.
and then go into THNOTL.
Okay. Yes. Here.
Just again paste this.
Yeah, it's coming now.
It is coming. Just double click it whether we can see it is so.
Yeah.
Yes. Yes, it is okay. Yes.
Good stuff. I was looking some example like how this works, because this is the first file I have seen with this leader propagation, and I think, and this is like kind of a advanced method to simulate this, rather than
Yes.
the volt curve. So I got some thing written on this book, Andrew Hillman. I think I also gave it to you guys.
Andrew Hillman, it is there. I hope this linear
Yeah.
progression method will be there in JC DOS too. Yes.
All right. I was not sure about that. I think. Oh, I think it was normal page 391 or something. It does explain it a little bit, but I didn't like invested too much time. But I just want to show you. I mean, if you want to implement it, you can probably implement it. It does explain. It does explain this here about this this method, right? Starting from here, LPM method, and it does give some calculation and this equation, and that's how these folks have calculated these variable like that gradient, like for
Alpha,
example,
beta, yes.
so that's the gradient they put here, and then gap distance or something like that. They definitely come up with something from here.
Scale. Yes, then we have to go through this completely.
Yeah.
Then we can see. Yes.
Yeah. So they definitely come up with something from here.
Okay.
I think.
But
I didn't open the JC Das, but this was a reference book, so I opened it and I saw like this is how they done it.
But I hope the what we say that the voltage which they are giving there and the gap distance, I hope that all remains the same for what we say that for the insulator, what is the breakdown voltage that we have, that they have to collect it from them. And then other thing is like they have to collect the gap distance from the gap distance for the particular insulator. That is what I have thought. The remains the same, I hope.
Yes. Yeah, no problem. That's what I wanted to show. Anyway.
Yes. Okay. We will go through this. You have shared this book. I will go through this, and I will. Today I have tried to go through this Monte Carlo, but I didn't have any time. So that.
Oh, I asked the PSCAD dude support for this. I just asked them like, can you tell me how do I do this this thing, in PSCAD. That guy replied saying that our lightning example is located here on this page, and if you are interested to do such simulation described in paper, please contact author. I'm like, oh wow.
Okay.
So I like, okay, that's great. So what that lightning Monte Carlo is, I think it's just like this example is done. I think in the same way we can just put like, for example, more iteration. So if we specify the surge, so instead incrementing the current, if we specify the surge using alpha beta method, for example, and for that alpha beta coefficient, we know like what is the alpha beta for example, positive peak, and what is for negative peak, and what is for subsequent stroke. So we can put like couple of variables to control them, and I think that's the only way to do it.
Okay.
And we can also
gone through, but as you said, he is just changing that alpha beta values for up to that. I have read some lines and I have understood that he is doing something like that. Yes. Other than that, I haven't read completely. If I have time to go through it completely, then I can come up with
There
some
is
solution.
one more example. I don't know how. Share share content, share desktop. I will open that again. I will tell you what I wanted to tell. So, there are so what I am saying is here inside this search, if we go here, right? So instead of specifying this method, and
Yes, yes,
if we go here, so
yes.
the search waveform, we can do the custom alpha, beta, or custom front or tail time, right? Here,
Yes, 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 yes. That
you
is
know,
what I have told
yes,
yesterday.
yes. So this front end wave time, either we know the positive stroke is something, so we can give a particular name from here, and we can control these two variable using the, you know,
Okay, okay. Yes,
using
yes. That is
using the
what we can
multi-run.
do.
Yes,
Yes, using
I
multi-run,
think, you know,
we can do
yeah,
it. Yes, yes.
yes. And then we can do, I think, that way, and we can same way we can control the tower footing
We
as
can
well,
control it.
and
Yes, yes.
we
That
can
we can.
control this as well, you know. So one for this, for instance, and
Uh,
then for one for this, and two for them. So four channel, six channel we can control. So I think
Which channel we can control? Yes, yes. That is
I
the
think
maximum we can do.
I think that's a way to do it. There is a
Good.
ATP example. If you have this software, it's hard to understand because it is not nice, but it does.
Yes,
Yeah,
yes, yes.
yeah. I tried to learn this on my own, but I basically went nowhere. So just wanted to show you that example. I can send you this example if you have the TP draw projects. I think it was example 20 or either of them. Yeah, I got correct one. So this is how they modeled it, but here they
Okay.
got this options already called right Monte Carlo,
Okay, okay.
right? So I have no idea what this is, but I can go through the help later on and I will try to
But
understand it.
we cannot run this module here, right? In this ADP draw.
No, I can draw it. I can run it. If I run it, it is going to, it is the license one. It is a free. So if I do like that, so you know
Okay.
what will happen? It will run like that.
Okay, okay.
So yeah. So uh, uh, uh,
How we can get this? How we can get this
this
software?
ATP draw is a free software. So
Okay,
the the
okay.
the interface you can download using, just say go to ATP draw or something. The only thing is you need a license for it. The license is again
Ah,
free,
yes.
but you
Okay.
need to obtain through ATP draw down. So ATP draw you can download from here,
Yes, yes.
right?
We
Yes,
have tried this, but what we have to do is like we have to send a letter to
a
them,
letter,
right?
letter to them.
Yes.
Yes.
From the
So
letter, we have to get confirmation from them. Then only we can use this. Yes.
yes, that's the only way to do it. But what I done is I downloaded this from here, and then I use the license provided by my company,
Okay,
because my
okay.
other
Okay.
colleague used this for some other studies,
Other
but
studies.
they only do the studies like somebody set up a template for them, and they are like
Mhm.
keep using it, so kind of thing. So they are not like on a very advanced
Advanced.
level.
Okay, okay. But
So
ADB draw is what we say that is the first software which has been developed before PSCAT. From there only PSCAT got developed like that.
yeah, last year I tried to learn that, but as
Uh,
I said, like I was only able to like model the source, load, and like transmission line and cable, but
uh,
doing a project was like impossible to understand like what the
yes,
software is.
it becomes somewhat bit difficult task to learn that software.
Yes, 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 yes. No problem. We can carry forward with
Yes.
our
Yes.
session.
Today we have planned to see very fast current over voltages.
Yes,
Basically, that is what we have planned to see. And if I have time, if I have completed that, then Gokul will take care about ferroresonance studies. Okay,
okay,
from there you will try to teach ferroresonance if we have time. Yes, but if we have no time, then if we don't have any time, then we will go with very fast current transient over voltage itself.
okay,
Okay.
okay. please.
I will share my screen and we will start up with some basics. Okay.
Yes.
I hope you can see my screen. Yes.
Yes. Yes.
My SIG model PDF document.
Yeah.
Yes.
I can see.
Yes. Do you have any idea about why we are we do need to perform this vffo studies? Basically, for where we have to perform this vffo studies. Do you have any idea about the
Yes,
VFPO?
it's yes in GIS due to as it is written there, yeah, due to disconnector operation, it generate traveling surge,
Yes,
and
yes.
that for that purpose we need to do this. Yes.
We have to do this, right?
Yes.
But I hope you don't know about the ranges of voltage where we have to perform SFO
Yes.
and FFO
From
is
I.
not there. Like
Yes.
that, you might know about that, right?
Yes.
The range one what they used to do is like they used to perform FFO only
Yeah.
because less than 245 kV SFO doesn't have that much critical
Yes.
impact,
Yes.
so
Yes.
they will stop with FFO only, like
Yes.
that I'm saying. Yes, yes. But what the general is like, whenever we have a this gas insulator switchgear, then we have to perform this VFPO
Yes.
studies. It
Yes.
is basic for all the
All the
ranges of
GIS. Yes.
all the GIS. Okay,
Yes.
and where we need to perform is like we have to perform this on gas insulator switchgears.
Substrate.
Okay,
Yeah.
gas insulator switchgears.
Yes.
And why what do we say that the main generator for all the VFPO is like we have other things also, like what we can say. Other things includes mm, like what we can say is like circuit breaker action.
Yeah.
Okay, circuit breaker opening and closing action. And other than that, uh, what we have is like circuit breaker action is uh, one of the thing where this VFPO may happen, like operation of circuit breaker and the occurrence of fault inside the JAS.
Yeah.
Okay, these are all the other things which what we say that during earthing switch operation, these are all the other things where your surge will also get generated.
Yes.
But what they have been saying is like the action which is performed, like the disconnector action, it is the most unfavorable condition, like that they have been saying. Okay,
Yeah.
in the that is why we used to perform the condition like the disconnector operation only. We will be taking it as an most worst case to perform the VFDO studies,
Yeah.
and then we will be simulating for the circuit action. Okay, that
Yeah.
is what we generally used to perform. Okay, generally what happens is like when we perform this study, what due to this closing operation, like switching of disconnector switches, switching of disconnector switches, what happens is like there may be what do you say that there will be some pre-strikes and restrikes. That is what they have given here in the
Yeah.
definition. I hope you
Yeah.
can see this, right?
Yes.
Pre-strikes and restrikes will happen, and then
Yeah.
what it happens is like there will be a surge between the contacts, right, at the
Yes.
time when the pre-strike happens. So at the time what happens is like the voltage collapse will happen
Yes.
between the contacts. We have two contacts. One is
Yes.
one side we do have a source, and other side we don't have anything. Okay,
Yeah.
there will be some potential difference, right? When there is
Yes.
without voltage, and what it happens is like there it happens a pre-strike and restrike will happen. So
Yeah.
that at the time that happens is like it will be in few nanoseconds.
Yeah.
It will be in few nanoseconds. Okay, at the time what happens is like your surges will be produced in the GIS.
Yeah.
Surges will be produced in the GIS. What will be the frequency of this? This frequency will be about 100 megahertz.
I love.
Okay, 100, it will be about in the range of 100 megahertz.
Yes.
Okay, and then this surges which has been transferred, what it does is like it will get deflected from the other open end, right? there we might have some open end, right? When we perform this disconnector action, what it happens is like your surge will be produced, and this surge will travel to an open end, and there it gets reflected and refracted.
Yes.
Okay, what happens when we get reflected and refracted waves?
Over voltage.
Automatically what happens is like there will be a huge built-in voltage, right?
Yes.
There will be a huge built-in voltage. That built-in voltage, what it does is like it will produce more stress on the insulation, right? We have conductors inside the GAS, and we have enclosure that
Yes.
has some insulation, what we say, that the insulation level, yes,
Yes.
that will be getting more stressed due to this action,
Yes.
due to this action. Okay, that is why we have to check whether this built-in voltage which is happening due to this disconnector action is well within the limit of lightning impulse withstand voltage.
Yes.
Okay, is well within the limit of lightning impulse withstand voltage. Okay, for this, with which bill we have to compare is like we have to compare it with the lightning bill.
Yes.
Okay, lightning bill. Okay, this action will become, what happens is like this action is very much severe when the voltage level is very high. When the voltage level is very high. For example, we have IEC 60071, right?
Yeah.
There they might given the over voltage for or what will be the over voltage for different voltage levels, right?
Yes.
For example, what we can take is like, for example, let us take 300 volt.
Yes.
Okay, 300 volt is the rated voltage of a particular 300 is the rated voltage of the particular station. Okay,
Yes.
there what will be the lightning impulse level? There
850.
what will be the lightning impulse level? It will
850.
be like 1050. Okay,
Oh
for
yes.
300 volt, highest lightning impulse
Highest
is
one.
1050.
Yes.
Okay, then what will be the ratio of this 1050 divided by 300? What will be the ratio? It will be in the ratio of 3:5, 3.5,
Yes.
3.5. Okay, but when we go above than that, above
Yes.
300 volt, what happens is like, for example, let us take 1200 volt.
Yes.
Okay, then there we can take 2700. Okay,
Yes.
2700 divided by 1000 through 2700 is the what we can say
Highest.
2700 is the lightning impulse for the
Yes.
voltage level of 1200. Okay,
Yes.
then what we can get only a lightning, what we say, that the ratio, what will be the ratio? My
2.25.
highest voltage is 2700. Sorry, my lightning impulse voltage withstand voltage is 2700, and my highest rated voltage will be 1200. At that time, what happens? What is
2.25.
the ratio? It is only in the 2.25 ratio. This is what happens when we go above certain amount of voltage. What happens is like, if you go further towards the greater number of voltage, what happens is like your ratio for the rated voltage and lightning switching impulse voltage will be getting decreased, will
Yes.
be going on decreased. So that what happens is like, whenever this what we say, that whenever this action is performed, like we say this GAS is performed, what happens is like your ratio between is getting decreased. The
Yes.
general, the voltage which is developed due to this disconnector action is will be in the ratio of 2 per unit.
Okay.
Okay, it will be in the ratio of minimum, it will be 2 per unit.
2 per unit.
Okay, for the worst case scenario, I'm saying, for the worst case scenario, it will be 2 per unit. Okay, at the time, what happens is like we have to make ensure that due to the disconnector action, it doesn't go beyond that limit, which we say it as lightning impulse withstand voltage.
Okay.
Okay, that is what we have to ensure by performing this very fast front over voltages.
Good.
Okay, I hope you got the basic idea for that.
Yes. Yes.
Yes, yes, okay. And other thing which I want to tell is like, we have discussed about why this vffo needs to be performed,
Yeah.
right? We have got that basic basic understanding why this VFTO has to be performed. And we have also seen like what are the causes of this VFTO,
Yes.
right? What are the causes? It may be due to the circuit breaker action, line to ground fault, or fault within the substation, earthing switch action, like that we have. But due to this worst condition, we have been taking disconnector option as the worst condition, and we are creating scenarios for that, right?
Yes.
Yes. And then other thing what we have to do is like we have to know we have to know what we have to know is like the different types of classification of this VFTO. Okay, we have to know what is the classification of VFTO. Just a minute, I will. Can you see this? These are all the classification of VFTO.
Yes.
Okay, the main operation, the main operation is like the operation of this disconnector. But what they have done is like they have differentiated into two types: internal transient voltage and external transient voltage.
Yes.
Okay, what generally happens is like internal transient voltage means we have a GIS, right? We have a GAS.
Yeah.
Okay, GAS will be an enclosed compartment.
Yes.
Okay, GS will be an enclosed compartment. Just wait a minute, I will show you some GS models also.
Yeah, I am aware of GIS. I have been into GIS.
Yes, yes.
Yes.
There we will be having like there we will be having some conductor in between the enclosure, right?
Yes.
Conductor between the enclosure. Okay, generally what happens is like this one I got it from the website.
Okay.
After the session, I will share it with you to know the basic understanding of how this compartment will look like if we have uh, different type of configurations. Okay,
Yes.
different types of configuration. We do have like what do we say that we have double breaker schematics, double bus bar schematics. We have one and a half breaker schematics, like that we have, right?
Yes.
And for that, if you want to if you want to know right how this compartment does looks like for the one and a half breaker scheme, and for the double breaker scheme, how this compartment looks like, with this we can know the we can know the difference. Okay, how this what is it, the bushing feeder will look like that we can. Okay, we can keep it up. What we are discussing is like we have been discussing about the internal transient voltage and external transient voltage.
Yes.
Okay, what we are telling is like how this internal transient voltage will be developed is like this is the voltage which is developed between a conductor and a enclosure, right? We have enclosure and we have a conductor, right? If there is any fault happening, or any what we say that any earth switch action has been performed, what happens is like there will be a huge voltage will be generated. Okay, that voltage what it does is like it is one of the it is the phenomena which gives rise to this stress in insulation,
Yes.
stress in insulation. Okay, and other than that, what we have is that we have other types like external transient voltage. Okay, we have only one part for internal transient voltage. Like as I said, when there is a fault happening, then there will be a voltage stress between the conductor and the enclosure. Okay, other part is like we have a GIS. Okay, we have a GAS substation. Okay, and then GAS substation will be connecting to the air, right? It will be connecting to a air substation. What we say that
Here in.
when the transformer is in the is in outside,
Yes.
what they will do is like they will connect it from the GAS to the
AIS part. Outdoor part.
yes, to the AIS port. What happens is like there will be a change in impedance, right? When
Yes.
there is a when they are going to move from GAS to AIS, there will be a change in impedance.
Yes.
Okay, at the time what happens is like due to this change in impedance, the point where these two points are joining, like we used to say like when we are joining cable and the transmission line, right?
Yes.
At the time there will be a huge change in the impedance, right? At the time what happens is like there will be a huge voltage will be generated. This transient will be generated whenever there is a change in impedance. That is what we call it as transient enclosure voltage.
Yes.
Okay, transient enclosure voltage. And other phenomena are like transient electromagnetic fields and traveling transient electromagnetic fields. What it does says is like in
It will.
stations we might have some current transformers, right?
Yes.
We might have current transformers, right? What it does is like due to this impact of this over voltage, what it does is like there will be an interference. Okay, there will be an interference inside what we say that this voltage will be getting transferred to the other side where we have the relays.
Yes.
Okay, where we have the relays. That relay will be getting affected due to this electromagnetic interference.
Yeah.
Okay, due to this voltage which is developed in here due to the disconnector action or some other action which is performed inside the GAS, this voltage will be traveling towards the point where this current transformers are connected. Due to this impact, there will be an
Stress.
yes, there will be an electromagnetic interference on the other side of the on the secondary side of the current transformers where we have some relays that will be getting affected due to this. It may go into some dangerous condition, like it may go failure also. That is what they are saying it as a transient electromagnetic fields.
Yes.
Okay. And other than that, what is like we do know this concept, right? Traveling waves on overhead lines. When the surge has transferred from the GAS, then we have any overhead lines means then it will travel towards the overhead line, right? If we have in the way if we have some transformer, like if we here we have taken right an example where the GAS is getting completed and the other side we have a transformer means there what happens is like they are moving from GAS to AS, right? From yeah, at the time what happens is like due to this change in impedance, the surge will be traveling. If we have transformer, this transformers insulation will be getting affected,
Yes.
right? I hope up to this point it is
Yes.
clear for you.
Yes.
Yes. That is what this is how they have differentiated between this internal transient voltage and external transient voltage.
Okay.
Okay.
Yes.
And other part which we have to see is like for the basic knowledge about this VFTO is like I will before that how we will be simulating the cases that we should know, right?
Yes.
We will be simulating the cases is like what generally happens is like when we are not closing the disconnector. Okay, let us say we have just a minute.
No problem.
I hope my screen is visible. Paint screen is visible.
Yes.
Yes. What we will be doing is like here we let us assume this is and this let us assume this is a disconnector.
Yes.
Okay, this is a disconnector. Okay, here in this side what we have source.
Yes.
Okay, this we have source. Okay, this source what it does, it will produce 1 per unit of voltage in this side.
Yes.
Okay, 1 per unit of voltage in the in the source side.
Yes.
Okay, now your disconnector is slowly closing.
Yes.
Okay, slowly closing. What it generally how this scenario can be created is like what they are saying is like when the disconnector has opened in the previous condition, what it does is like it will leave out some trapped charges in this side.
Yes.
Okay, this part of the station. This trapped charges, what it can be up to 0.8 per unit. Okay, I am saying the maximum limit. Okay,
Yes.
this will be the maximum limit which will be there when in the case of this disconnector opening condition. It will be lefting out some trapped charges on this side,
Yes.
this side. But what they are telling is like to come to get a worst condition. What they are telling is like we have to assume there is about 1 per unit amount of trapped charges on this side.
Yes.
Okay. Now when we are performing this disconnector action, this 1 per unit voltage and this minus 1 per unit voltage will be coming in this location. Okay. Due to this action, what happens is like there will be a huge voltage build up here. Okay. This due to this voltage build up, when the here we do have only gas material, right?
Yes.
Gas material has some what do you say that some resisting property, right?
Yes.
It is an uniform field which does provide some resistance. When there is when this resistance gets break, what happens is like there will be a strike in this condition.
Yes.
Okay, this strike, what happens is like it will travel towards this side.
Yes.
Okay, due to this, what happens is like your what you say that due to this condition only your voltage is getting created. Over voltage is getting created. This action will happen within nanoseconds.
Yes.
This action will happen within nanoseconds. The voltage which can go up to 3 per unit.
Yes.
Which can go up to 3 per unit. Maximum of 3 per unit it can go. Okay, this is what this is the basic thing which we are going to do for the simulation purpose.
Yeah.
I hope you can understand this point.
Yes. Yes. Yes.
Yes. Can you tell me your understanding? Because this is the basic point which we have to take into consideration before going
Yes. Yes.
further.
So
Yes.
yeah. So you are saying that there will be a voltage on the either side of this longitudinal insulation, which is gas, and
Yes.
if we perform the disconnector operation, then that is going to build up sum up with a high value.
Yes. Yes. But
Yes.
not in the both sides there will be no voltage. What
Yes.
it does generally we are thinking is like this is a trapped charges.
Trap
We
charge.
have
Yes.
trapped charges. Yes, trapped charges. This
Yeah.
trapped charges will be we are assuming like it is in the range of minus 1 per
Minus
unit.
1 per unit. Yes.
Yes. Due to this action, what happens when we perform this breaker closing action?
Yes.
There will be a strike will be happening once the gas medium is getting break. At the time, what happens is like your surge will be traveling towards
Yeah.
the point
Point of impedance
on the
disconnected. Yes.
yes, both sides the surge will be traveling. Once it sees an open end,
Yes.
there it
It
will
will
be getting
reflect.
reflected,
Yes.
and it will get again it get refracted like this. The voltage will be building up.
Yes.
Okay,
Yes.
this is a basic thing, and other thing which I want to tell you for the basics is like other thing which I want to tell you about the basic is like let us take these two conditions. I hope my screen is visible.
Yes. Yes.
Let us take these two conditions. Okay, this is an GAS. Let us assume this is an GAS. Okay. Hello.
Yes. 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 I can hear you.
Let
Hello.
us yes.
Yeah.
Let us take this is an GAS.
Yes.
Okay. This is a what you say that this is a radial port like
Yes.
this.
Yes.
Okay, but this GAS has some T junctions in it.
Yes.
Okay, T junctions in it. Let us say for the this type of breaker configuration. Let us say this type of breaker configuration. If
Yes.
we made there will be some this what we say that this T
Discontinuity.
junction will be
Yes.
there will be some discontinuity. Yes, that we
Yes.
say it as T junction. Okay,
Yeah.
when we meet this T junction, what happens to the voltage or the surge? How it is getting reacted? That is what we are going to see with this example. In
Yeah.
the first example, what we have is like we have a radial system.
Yeah.
Let us assume this is a bus bar. This bus bar is about 5 meter length.
Yes.
Okay. Now what we are doing is like we are meeting a T junction. Okay, we are meeting a T junction and we are measuring the voltage at this point. Okay,
Yes.
after 20 meters. And now here we are measuring the voltage, which is U.
Yes.
Okay, at the first condition, what we can do is like we have a voltage source. We have a voltage source, which is an ideal source.
Yes.
Okay, which is an ideal voltage source. Okay, what generally happens according to you? Can you tell me what generally happens now? Whether this point here the voltage will be higher or here the voltage will be higher.
The voltage will be higher in
Which voltage will be higher? That is what my
higher.
question. Which
It,
question will
it will
we
be
can take?
higher in the second case, I think,
Yes, it will be higher in the second case, but why?
because there are more discontinuity and there will be more reflection.
Yes, more reflection and refractions will be there. So what does
Yeah.
happens is like your voltage waveform will be getting
Lower. Yes.
more distorted, right? So this distortion, like what generally happens is like due to the meeting of different types of impedances on its way, the voltage will be getting more reflector and refractions.
Yes.
So that what happens is like here the voltage waveform gets will be in a uniform condition, right? Since it
Yes.
is not meeting any what we say that any difference in impedance throughout its point, what happens is like it will be in a uniform
Yes.
manner only. There will be no distortions in this waveform, right? But
Yes.
here what it does, here there will be what do you say, that reflection refraction. So that what happens is like here the voltage will be getting more distorted. Now we will say the now we will see the outcome of this example.
Yes.
Okay, with the ideal source. Now what we have an ideal source.
Ideal source. Yes.
Yes, can you see this? This is the outcome of the
Yes.
example which
Yes.
we have seen now. Okay, here can you see this? It is the case one. Blue
Yes.
color is the case one. Here
Yeah.
can you see this? The
Yes.
voltage waveform is more uniform.
Yeah.
It is in more uniform manner. Okay,
Yes.
and because why it has not met any change in impedance on its way, so that it is more uniform in this condition.
Uniform. Yes. Yes.
Yes, but due to these discontinuities in the
Yes.
second case, what
Yes.
happened?
It is
What
higher. It has a distorted
it has get more
distortion.
distorted,
Yes.
and now what happened? The voltage which has been built up in a system is like it has
Higher.
gone up. Yes, it is just between 4.5 and 5 per unit.
Yes.
Okay, it is per unit. This voltage will be. So what we are coming to say is like the modeling which we are going to perform. Sorry, the modeling which we are going to do for the gas insulated substation
Yeah.
should be more precise. Okay,
Yes.
then only
It should.
we can see this much of variations.
Yes.
Whenever there is a discontinuity or whenever it is meeting some junctions, there the
Yes.
voltage will be getting what do we say, that will be getting reflected and
Reflect.
refractions,
Yes.
so that this voltage will be getting higher and higher.
Yes.
Okay, this is with the example of ideal source.
Yeah.
Okay, generally this much of voltage will not be generated in the system.
Yeah.
So what they have saying is like you have to model it as an what do you say that with a most realistic source with
Yes.
a ohm of 10 ohm
Resistance. Yes.
with some resistance. So that what they have done is like they have done the simulation again, and they
Yeah.
have got the output as why this waveform has distorted, why this waveform has got here you can see this, there is no damping in the system, right?
Yes.
There is no damping in the system, but here you can see there is damping in the system, right? Why there is damping?
That's because of the source impedance. Like.
Yes, source resistance, and also we have resistance here, right? So that
Yes.
what has happened is like this waveform has got damped again.
Yes.
It has drained out,
Right.
right?
Yes. Yes.
But this waveform, can you see this? This is getting this what we say, draining out, but they have not shown the complete waveform. It might have drained out in some other point. Okay.
Yes.
Here it is getting, but the here can you see the difference? Here the
Yes.
rise voltage is like here it is in the range of 4 to
Five.
5,
Five.
but here it
Yes.
is in the range of 3.5 to 4 per unit
Oh,
only.
yes.
Okay, this is one of the main thing which we have to take into consideration while we are modeling the gas insulator substation for the VFTO studies.
PFT. Yes.
VFTO studies. Okay, these are all the some basics before going into the modeling perspective of VFTO. Okay, I hope
Yes.
you have some basic idea about how to model this VFTO gas insulator substation. Some basics about VFTO, right?
Yes. 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 I
Okay.
have. Yes.
Yes. Yes. Then other thing which I want to tell you is like how we are going to model each and every equipment for
Yes.
the GS.
Yes.
GS. Just a minute. Just a minute.
Give me 1 minute.
Yes, yes.
Yes, Venkat. Hello.
Yes, yes. I'm just taking
No problem.
water.
No,
Yes, yes.
no problem. Is there like very warm?
Sorry, sorry.
Yeah.
Is there very warm in
It's
India?
like,
Chennai?
yeah. Sorry.
Is there warm in India? Like
Okay,
temperature?
okay. Is it warm in
Temp-
India? No. Some part of the in some part of Tamil Nadu it is we are getting more rain, and some part of Tamil Nadu it is more warm. No.
Okay.
Yes, yes. Change in seasons has been there. Yes.
My highest temperature is going 14 degree and people are feeling warm.
Okay, okay.
Yes.
Venkat, like, let me take a fraction of second just to understand how this is specified as a part of gas insulated switchgear requirement as a VFFO, and probably all other studies as well. Then you can just take it.
Sure, sir. Sure, sure, sure.
Yeah. So this is the circuit breaker requirement as a part of a gas insulated switchgear.
Okay.
So this probably means what say, as you know, like means what say, country to country, utility to utility, it will vary.
I
So
very
it
much.
is like a gas insulated switchgear specification, but like what we are literally means what say going to look at is like what with respect to the specifically to this VFFO, or probably what are the studies which we need to do and how they are specifying. Anyway, I guess this will be there with you, or probably you can just go through it, and probably means what is relevant for us, like we can really pick it up.
Yes.
So I mean, what's the when it comes to this studies, like just let me check quickly. Just second, like VFFO we put
It could be VFTO here. As of this.
right. Right. So I mean, so to say this is specified here as a part of the HV circuit breaker operating and mechanism, right? So these are all I mean, what say the standards that these etc. But probably means what say this is basically talking about this means what's the requirements of the circuit breaker.
Yes.
Like means what say they are talking about all these studies, just not the VFFO, but just quick have a quick look at it how it is.
Yes.
So circuit breakers shall be designed to withstand the over voltage impact during small inductive and reactive current switching. This we are going to see as a part of TRV studies.
Yes.
Okay, so that's I mean from this we can understand that that's a part of TRV.
Yep.
This capability shall be proved by satisfactory and valid test evidence in accordance with an applicable IEC. This capability shall be provided by satisfactory and valid test evidence in accordance with applicable IEC, which means like you need not really perform any studies. Okay, so probably you can understand this. This just says as per IEC. It is not really means versus saying anything additional. Okay.
Yes.
In any case where the CB fails to meet this requirement, suitable devices shall be equipped to control the switching timing and limit the over voltage resulted from the switching. That's like point on wave switching
Yes.
or something might be needed when you are, I mean, so say failing to prove this. But really, they haven't asked any specific study for this, like whether TRV to be conducted or not. So here, like a study is not really envisaged openly in the specification. Maybe customer may ask at last, but openly it is not there. They're just asking with respect to the standards, and if you fail to meet, then probably you need to I mean if you're not really meeting the IEC standard breaker values like TRV, triple RV, then you need to perform a study to prove that that is well within this breaker capability.
Yes.
The contactor shall ensure very fast transient over voltage. So this is a by default line which you will find it out in all the gas insulated switch gears.
Yes. I have seen that.
Yeah, I guess like means Venkat might have told means what say VFFO is applicable or VFTO is applicable only for GAS,
Yeah. Yeah.
not really for AAS. So this line invariably you will find, and probably you need to perform VFFO even if the customer is asking that. That's I mean what say no other go, right?
Yes.
And means what say in the setup envisaged in particular substation. So means what say it should be less than the specified over voltage. The contractors that carry out the study for each substation for which 400 kV GAS to be supplied to demonstrate the fast transient VFTO generated by the circuit breaker operation, slow operation of disconnecting switch. So I guess like when Venkat has talked about what's the sources for this, it's predominantly like a slow operation of disconnecting switches in the GAS. Correct,
Yes.
no?
Yes.
And it could be also because of high speed earth switches.
Absolutely.
Right. So you may be aware like why do we need a high speed earth switch? That is basically to convert the means was ungrounded issues to a grounded faults, right?
Grounded.
Yeah. So the GAS modeling study shall also include probable switching scenarios of the substation. The study report design calculation results shall be submitted for approval. Also, means was say here it's a tricky point. Like GAS modeling study shall be include all probable switching scenarios of the substation. So when it comes to like this, whether the switching is SFO or TRV is a question. You got the point. Now, GAS modeling studies shall include all probable switching scenarios. Yes, we are doing this whether it is for VFTO or probably is it a switching or is it for TRV is probably means was that that's not explicitly there. So I means we can interpret anyway, but means also if any study to be done probably means they might be means was explicitly telling as well in some of the cases. But here is what I just means was interested with respect to your study. Like when CDGS comes, I guess this is also part of this one, right? The study
Yes.
report design calculations submitted for approval. Also, GS will be designed to minimize the effect of transient enclosure voltage. Correct. This you will be doing using
Yes. In CDAX you do very simplified model. It doesn't include like any form of like disconnector or switches or anything. All you do is model the below ground dense mat, and it again varies manufacturer to manufacturer. For example, ABB might say like you need to put a high frequency dense mat using a mild steel conductor on top of the earth mat, and then some other guy may say like you need to put that below your earth mat, the high frequency net, and then you need to connect all the discontinuity point in the GIS to that particular earth mat. That includes your high frequency earth mat, that's what they call it, for to kill this transient over voltages magnitude or to help with it. And then another part is the power frequency earth mat, which is 50 hertz earth mat, which is there to protect like touch and step. So we model this below ground scenario, and then above ground GIS we only model three phases approximated as a cable, because that's the only way to model in the CDGS. And then for a person standing near GIS or person touching two part of the GIS, that's how we calculate the touch voltages, metal to metal or GIS to like normal standing, normal touch voltage. And then in terms of transient requirement, there are not like a magnitude or surge specified as Venkat cleared in the beginning for the VFTO. So it's really like you can put like a generic switching waveform from standard with some front time of like 250, another is like 2500 or in a different scenario, and then just inject it with a maybe 1000 kiloampere or something and just try to get a magnitude of what is again the enclosure voltage. That's how it done in CDEX in very simplistic way.
Yeah, right. So means what to say? You will not model anything on the GIS equipments in CDEC then.
No, it's not possible. It's not possible. Whoever is saying you to
Understood.
like these things, it's just a myth because they just made it up.
Yeah.
There is no way to model any of the devices other than the conductor. You can model everything either as a cable, either as a conductor. That's it. There's no other provision to model, for example, a surge arrestor or how surge arrestor will operate. You know, you can however model the transformer as it is, as like three windings, or two winding or jig-jag or Scott connection or anything like you can model.
Right. Okay. Fine. Like means what's when the other things also there, like I mean, so what do you say? The sun reactor switching specifically, that I guess one day we have introduced this point and wave switching, right? So that also probably there. Like I guess this document might have been shared. If not, like I'll share this portion so you can just quickly look at how to relate the specification of the GIS and decide like what are the studies which we have to carry out as a part of the scope, though they not explicitly say. Like
Yes.
means also the study which will not come explicitly, like these are the studies which we need to perform.
Yes.
And means we need to probably means also like this words we have to understand like what are the things which has to be done. Like means here they are telling means what say this reactor switching device shall be provided so that like the voltage is below 2.3 per unit, something
Yep.
like that. So I mean then what's the feature which need to be, so like everything we need to carefully go through this portion to decide like what are the studies which we need to perform.
Okay.
Right. Yeah. Yes, Venkat. You can.
You want me to show what we model in serious? Like, we'll do it later on.
If you have any time.
Yeah, I have one example I can
But
quickly show
what
you.
the transient enclosure voltage? What I have understood is like it is the voltage that is built in between the external part of the enclosure and the ground and the earth part
Yes,
of, yes,
that's
that
right.
is the
That
earth,
is
that is called, we call it as transient enclosure voltage. Yes.
that is basically a ground potential rise of or a normal, like for the power frequency fault you are saying is earth potential rise or GPR
Ah,
of that enclosure. In the same way you are saying that more precisely here, like transient ground potential rise, because that's what happened because of the transient.
okay.
Yeah.
Yes. That is
So
what
that
I'm saying.
yeah,
Yes.
that is the only one like I would say is a difference. But in the CDGS you can't model like so many
Okay.
things. You
How
can
we have to call it as? Then how we have to call it as? We say it as transient enclosure voltage. How you guys are used to call it as? What do you say?
it's called we call it TGPR, transient ground potential rise.
Transient ground potential rise. Okay.
So
Yes.
I can show you this a file I used as in last 2014. It was like an example that has everything. So
Okay.
can you see my screen all right?
Yes, I can.
So what it is basically this whatever you can see here is a pipeline. So I will delete this line. So here we modeled a voltage source with a 500 kV transmission line
Okay.
and with all the towers and everything, right? So
Okay.
you can see here the energization, it will be like 500 divided by 2 3 or something, right? Then when it comes to the substation, so we model these gantry just here, and after that these are modeled as a cable. So if I click this right click, so it tells me that sorry, it's grouped ungrouped. So it tells me that this is a cable type, right? And if I
Okay.
go in a cable show cable type, so it tells me that that was the cable defined with just generic parameter like core sheath, inner radius, outer radius, same as others. It's just a different interface. It's not like
Okay.
something very different, right?
Oh.
Then what happened is when it comes here, then it goes to this transformer, right?
Oh.
So this is a transformer
Okay.
here, which is converting 500 kV to 225 or something, right?
Oh.
I don't remember, but yeah, this is what it is. Yeah, so you can get these transformer insert and then a object from database. So here you can get so many things like 3-phase transformer model, or you can get this lossless transformer on, or so many things, right? So that's what it is here. And then after that, it is going to a building where this GIS is. So this everything box is basically building. So I delete that, right?
Okay.
And I also delete that. It is a shielding structure of substation. Now you can see better, right? So
Yes.
so this is ArthMat, and
Okay.
this is a GIS, right? So what GIS is modeled is basically a cable enclosure inside that 3 cable. So they model the GIS like this, and then 1, 2, 3, right? 3 phases, 1, 2, 3.
Okay.
So that's how it is modeled. Now,
Yes. This is how it is.
yes,
Yes.
yes,
It will be.
it's just approximated, I would say, right? So
Okay.
again, I go to cable type. So this is GIS cable. So you see
Yes.
RYF 3 phase, and then they will be inside one main enclosure. That's I explained, right? Then what happened is this is for the power frequency fault, by the way, not for transient, but what I'm showing is how you model a GIS in CDAC. So you really need to have a 3D drawing, like how it comes here, goes, and all the discontinuity and everything.
Okay.
Then here, after that it goes to here and to a local load here, and then goes towards another substation, right?
Yes.
So this nobody does like this much detail modeling, like these
Okay.
transmission line and everything. It is only like who is SES employee or who know like software on very advanced level. Only they do it. Other people will just create something like this,
Okay.
right? No transformer, nothing like this, just ArthMat and this GIS, for example, right?
Okay.
So in this case, if I model this or if I don't model this, make no sense.
Yes.
This will only work if I create a voltage source like I did before. And then in that case, my source is there and I can create any fault in the substation and I can generate the same phase to earth fault level like the utility gave me. And then the idea is because there is a IEEE 80 document, so it says that you need to investigate 3 fault in this GIS. I can quickly these are all the copy that I got from somewhere. No, it's not mine. Some I don't know if I have. Sorry, that's here. So this IEEE 80 has a 3 requirement, and that's why the people model it in the GIS. There was one. This one, sorry. So here, this is how the GIS is. So this IEEE says like what you need to do is you need to put one internal fault inside this tube, inside this metal enclosure, and one fault from enclosure to ground, and another is a remote fault, and they all fault should say like your all voltages are same, whether you stand here and touch this GIS same, or whether you stand right in the middle and touch this GIS and this GIS together, for example, 2 parts of the GIS. So for that purpose only, this is required, right? So that's why the people model like this, no transformer, nothing like that, just a mat and with this, and that's how they calculate. So I can in the software plot the GPR or the metal voltage of this enclosure, and I can say, okay, if you stand here, if a person stand here, so he's going to subject it with that particular metal GPR, you know. So that's how the people do it. You can also model a human being here, a person with a approximated impedance, and then you can also calculate like what goes through that person body. Maybe one second. That person is approximated as a IEEE human circuit or something.
Human circuit. Okay.
Yes. It may not have it. Yeah. I done one tower TP. So what I do here is, this is like a person, you know.
Okay.
So I can copy. So before I copy, I can show you another better. Yes. So this is an example where there's a tower, and if this is faulted, so if guy is holding that, so precisely instead of, so if I don't model this guy, I can model the touch voltage based on these point called profile, which means just imaginary surface where you are standing, right? And I can plot it in software. More precisely, I can model this guy here, and I can give it some impedance. So for example, here, these legs is modeled as a 2000, and this is modeled as a 1000. So 2000 parallel to 1000, and then this is 1000. So this 1000 is a body impedance, and these two impedances are put here to represent the shoes, right? The footwear. And what and whatever resistance you will automatically get due to the soil, that is represented by this disc, you know, to represent it like your normal feet. So it is like, and then I can run the software and I can see what is the current flowing through the person body, and I can calculate it. So the same person, I can group it, and I can copy and paste, and I can dump that guy here in the GIS, and I can put here right in here, and then I can put that one hand here, and I can show like what is the issue. What is the problem? Another example on that. If I have that. Yes, so it is just approximation. It is not as detailed as this particular software EMTP. So one more example you will see here is it is an example of a fence. So that's again a guy, and you know how the fences are near substation.
Yes.
So if this is a fence, so if this guy is walking around the fence, and this is a high voltage line right next to the fence, so it will induce some volts on the fence, right? So if a person touching this fence, then what happens to him? So these are the always everything is like, everything is a conductor. There is no particular device other than transformer.
Yes. Okay.
Other than transformer, you can't model anything in here. So that's how this works. If you want, I can send you some paper on those are done by CDEX for your understanding. But I don't do anything here like these. I just model the normal GIS, and I can show you one example. Actually, this one just I am running now. It is depend on the manufacturer to manufacturer, and it depends on the folk like who are asking you to do this study, how knowledgeable they are or what they want from you. So this is one example I am running just now. So it is a big 400 kV substation, and in this substation there are two GIS, right? So if I go here, this is a ground floor GIS. So whatever this red I selected is basically a rebar representation, and this is what this another thing is basically copper mat, right? So that's how they installed in the field, and that's how I modeled. But if you go here, there is a 2-floor GIS. So this is a ground floor, right? So this is just a rebar representation. I modeled very less, and this is a copper conductor. Same in the GIS, what they say is basically, this is what I selected here in this view. You can see better. This is a rebar, floor rebar. The you means the rebar, like the metal. Then after that there will be some cement and
metal
concrete.
Means it is a floor, just a floor.
Yes. No, floor rebar. The metal. Yeah, the metal. You put in your like foundation and everything. Same thing, like you put a steel pile or big rebar on the floor to support the floor, and then you will pour the concrete, cement, and everything in this gap.
Yes.
So So what happens in the field is like some manufacturer says this copper mat, which you can see on the top now in the 3D view, you will see like that, like this, only this much limited, run on the GIS surface. Probably you can also see the shape, like this is how, you know, the GIS will be structured in this area. So they say, manufacturer to manufacturer, they say put this concrete mat on the top of this rebar on the floor, final floor, right? And then earth all the GIS on it, right? Some manufacturer says if you are a first floor GIS, this copper mat should be below this, right on here on the ceiling, like your ceiling fan. Ceiling,
I got it.
yeah,
I got it.
So it, so it should be right stick to this floor. So then in that case I will model this down, and to calculate any voltages here, then what we do is one imaginary surface we calculate, like this called profile point, and then I can calculate the voltages. So that's how I do it. I don't model any GIS or nothing like that, because these things are already, this VFTO and TEV already captured by like EMT software. So here all I care is what happens to the power frequency voltage. So SES wanted people to model this as well based on IEEE. First thing is we don't follow IEEE here. My standard does not say anything like that. But even if you want to model this or do something like this fault, so it makes sense only if you model everything with the right voltage source and everything, and then you simulate the fault, or somebody gives you the right fault current for the enclosure fault. In India, people are using just 63 kiloampere or 33 kiloampere, just with, you know, the circuit breaker rating, like the equipment rating current. So in that case, whatever you do is waste of time. It doesn't matter.
Got it.
Yes. So this is how folks model, and because the amount of conductor you need to run, you will see this is running for last 24 hours. And this will take another 1 or 2 days. So this will finish over 3 days or something. And that is only because this model is a high-end module, and as the number of conductor increase, the accuracy increase, but then it takes a lot of time. Yes. And in this CDAX, to represent any wave, there is a one module. It's called, I can show you later on once we go there. But this is in this module, this is based on the Fourier transform. So what we do is basically in forward Fourier transform, we specify a wave. So if you are specifying lightning, you can specify only like standard lightning wave, Helder, or double exponential. And then if you go for the GIS like VFTO or something, then what we do is like we just put the single RLC switching, or we will specify surge, and we will put some manual surge here based on the standard. And then we will apply this response to that system, and then that's how we calculate. Like in inverse, like you can calculate again touch, step, and electric field and magnetic field, and only some of the quantities. Like this is the old interface, but in the new interface it is very good. And once we finish our classes, I can show you one quick example like how to do that. But this is all about GIS from earthing side.
It is all for the safety purpose, right?
Yes, safety purpose as well. And the dense mat I was showing you, the intention I was showing you that because you need to put that dense mat below the GIS. And who tells you that? Yes. Who tells you that? It basically manufacturer, not the owner, not the utility owner or the substation owner. It will be the guy who manufactured that GIS, who supply GIS. They will give you earthing specification, and they will tell you that the power frequency earth mat should be copper or steel, either way. Or and then high frequency earth mat, they call it, and they will say this high frequency earth mat should be below the power frequency earth mat, and this should be conductively connected to a normal power frequency earth mat with every 3 meter or 1 meter or 2 meter. And they will also give you a diagram. I will share one ABB specification for that I have got for UK. So then it will tell you that you need to earth your cable on like every cable cubicle, every like discontinuity, like, as you know, the junctions and stuff like that, and you need to earth your low voltage surge like that.
That is what.
So it is there for like power frequency fault, but like you explained in the beginning that there will be some electromagnetic interference. So because three phases are so tight together in that metal pipe, so it is going to induce a lot of voltages on the enclosure itself and on the ground itself, you know. So it is for that purpose as well, to protect the people. And like you are explaining the VFTO, so it is also up to a point to suppress that as well.
Okay.
But we don't do anything with it. Nothing.
Okay. I don't know this much of information, but yes.
No, it is because some people think earthing is just a joke. Like, you know, they think like if you are doing earthing law, you can get an Excel sheet and do it. But that's not how it works. Unless somebody died, you know, nobody cares. And especially like in our country, unfortunately, the people don't care much health and safety. But here in like these Western countries, it matters a lot, because if something happens to someone, an incident, and it's because of you or because of someone, then they can put your director behind the jail, you know, behind the bar.
Okay. The man
They can shut down the full company. Yeah. Yes, it's
yes. Got it.
So that's why this I will give you guys one or two specifications that tells you from two different manufacturers. Like you will see that there is a different practice of earthing.
Okay. If you have any information regarding how to understand these basic things like earthing, if you have anything,
earthing is again, you know, I can tell you the thing and I can give you the stuff, those two specifications. For example, GIS, so you will understand what are these and why we are doing this all. You doing VFTO in EMT, for example, you know, so you will also see the other cause of it, like how this study or how is interrelated to another part, you know. So so I can give you that and couple of paper as well. But at the end of this one, I can show you like what are the key things that you need to consider for the earthing, and when it can go better and when it can go worse. The understanding is simple, but again, the experience you will again like got so many experiences like you know, this load flow and this you know, insulation coordination. I don't have, because everything I done is earthing. And then same way, like you never done earthing, so you don't have any experience on that.
I don't have any experience regarding that. If you got any chance about reading some basics about it, yes, it will be good. Yes, I may try to know what is the other side.
Last one day we can keep for that, and I can tell you right from the beginning, right from the scratch, what it means and how you do it. And if for example you guys are going to buy CDEX or going to do that in ETAP or other software, what are the key things you need to consider and what can catch you in general, you know? But whoever says to you like I have done some magical job in CDEX or anything like that and I model GIS and this and that, just ask him simple thing, give me the file and then I will see like what it is. So once you open the file, you will see that guy just because the person who is sitting in the electricity board, he don't know anything. Only he knows CDEX is a good software or ETAP is a good software, you know. So only they see is nice results, like nice plot and everything, and rest they don't, you know. So that's how it is, unfortunately. But I will give you those
some basic
some paper.
Yes, thank you. Then
yes,
shall we go to the
yes.
Share my screen. First of all, before going for that, I will tell you what are the data which we have to collect from the customer to proceed with the VFTO modeling. Okay. For that, what we want to get it like, just a minute. It is just a minute. It is getting hang. Yes. Can you hear me?
Yes.
I hope my screen is visible too. Yes.
Yes, I can see.
Okay, before going for the VFTO modeling, I will tell you some basic things like what are the data which we have to collect it from the customer. Okay, the first thing which we have to collect it from the customer is like this drawing, this input insulation. I hope
Yes.
we have seen this
Yeah,
drawing,
we
right?
discussed
For,
this. Yes. Yeah.
yes, this data we have to collect it from the manufacturer of the particular GIS.
Yes.
Okay, like this data we have to collect it from the customer.
Yeah.
Okay, and then here you can see this data sheet does provides all the information, like how
Yes.
you have to model a particular circuit breaker, how
Yeah.
you have to model a particular disconnector and earthing
Yes.
switch, current transformer, GS bus tech. How you have to model that, this depends. Okay, this input we have to get it from the customer. Okay, and then the other important thing is, if the customer has not provided this disconnector action,
Yes.
okay, this combined disconnector, here can you see this? This is basically this input is only for the very fast
Yeah.
current transmitter.
Yes. Yes.
Okay, like this like this input you have to get it from the customer.
Yes.
Okay, like they might have specified the capacitance of that they might have said what is the resistance that we have to take, how this what do you say, that how this disconnector will act, like the data which we have to collect it from that. Okay, this is the data which they will give it to us. Okay,
Yeah.
and the other thing which we have to get it is like, this is one basic information. And other thing which we have to get it is like, we have to get the GIS model.
Yes.
Okay, GIS model from the customer. Okay,
GIS model
is
means you means the length and height and everything of this physical
just
structure.
GIS model means it is a complete GIS model. The what we say, that the 3D view of the
Yes. Yes.
GIS.
Yes.
That is what I'm telling.
Oh, it's 3D view, right? Okay.
Ah, yes. I will go into the model.
Yes.
Can you see this?
Yes, I can see.
This is a complete GIS. This is a complete GIS.
Yeah.
Okay, this is a complete GIS. Here, can you see this? There is something like lines.
Yes.
Okay,
Yes.
this
Yeah.
line
Yeah.
just represents the GIB.
Yes.
Okay, GIB
Yeah.
of other particular GIS. Okay, these are all the GIBs.
Is
One,
that
two,
is that a
three,
3D view?
four.
Mm.
No, no. I hope it is not a 3D view. It is a 2D view.
Yes. 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 Yeah.
It is a 2D view. It is a 2D view. If you want the other views, that we can get it on the next sheet. Like on the layout sheet, they might have given the other view also. You see
Yeah.
this? They have given the cross section view, right?
Yes.
They have given the cross section view. Like that, we can get it from them.
Yes.
The thing which I want to, which I have came here is like, if you are going to model the GIS, okay, if you are going to model the GIS, then we have to model this GIB also. For that, what we have to do is like, we have to know the length of this
Land.
GIB,
Yes.
length of this GIB. Not only GIB, if we have some bus bar between them, this is a bus
Yes.
bar. Okay, this is a general bus bar. That bus bar we have to model.
Okay.
Okay, for that what we have to do is like, we have to take each measurement of this bus bar and we have to include it in our studies. Okay, we have to include it in our modeling in PSCAD. Okay, for example, hello.
Yes. Yes.
Okay.
Yes.
For example, here what we have is like, here we have this is an transmission line incomer.
Yes.
Okay, this is a transmission line incomer. Okay, this and this. We have two transmission line incomers, so that they have given like this.
Yes.
Okay, two transmissions line circuits, which is L1, L2, L3, and this is
Yes.
L1, L2, L3. Okay, it
Yes.
is a double circuits. For single circuit, we can take this, and for other circuit, we can take this.
Yes.
And in the project which we have shared, we have like three cable incomers, like
Yes.
three
Cable.
cable
Yes.
incomers. Where it is number one.
From. Yeah.
Just a minute. There will be some future times. Yes, these are all some future works. This is ours. This is one. Okay,
Yes.
this is one incomer.
Yeah.
Okay, and other one incomer is this one, this
Yeah.
incomer, and other incomer is like this. This is
Yes.
third one. Okay, we do have some 3 cable incomers, and we do have about 2 transmission line.
Overhead line, yes.
Overhead lines, yes. Overhead line incomers. And other than that, what we have on the other side of the
6 outgoing.
Yes, 6 outgoing feeders, right? We have 3 transformers, and we have about 3 reactors, right?
Yes.
So that here, can you see this? They have given some 3. This is 1, 2, 3,
Yes.
4, 5, 6. 6 numbers of. Yes.
Yeah.
This is generally for transformers, and this is for the reactors.
Yes.
Okay. Here they have 3 transformers and 3 reactors. They have shown 6 GABs for that. Okay. For that, what we have to do is like we have to model this GAB, right? To model it completely. For that, what we have to do is like we have to take measurement of each distance.
Yes.
Okay. We have to use this distance option. Okay. And we have to select this center point. Okay. Center point to this point.
Yes.
Okay. If we set this, then in the below we can get the distance. Can you see this? It is 287 meter. Okay.
Yes.
And then for this distance, what we have to put is like here we have to put some one surge impedance.
Yes.
Okay, we have to put one surge impedance. And other than that, here we have some L bend. Okay, we have elbow, right? So then what we have to do is like we have to take measurement from this point.
Yes.
Okay.
To the further.
From this point to the other elbow where we are going to move. Here, can you see this? There is some elbow. Okay, up to this point we have to measure it, and for this location we have to measure it as some surge impedance.
Yeah.
Okay, for this particular distance. Like this, you have to model the complete substation.
Yes.
Okay, complete substation. Okay, this is for the view of what we say that for modeling the GAB and those things. Okay, for equipments, what we can do? For equipments, we can follow this, right? We have got the data from the customer. Like we have for circuit breaker, we have this much of data, right?
Yeah.
Yes, this is for the circuit breaker. For the circuit breaker, they have given the model, right? How we have to model the circuit breaker. For example, how we have to model the circuit breaker is that, okay, so how we have to model the circuit breaker?
Yeah. With a line and then this is our capacitance.
Yes, this is something that it just refers to the contact of the circuit breaker. It is one contact and it is the other part of the contact. In between that, what we have some, if we have some open contact, means there will be some capacitance between them. That is how we have modeled this circuit breaker.
Yes.
Okay, this is how we have modeled the circuit breaker. And if we are going to bypass, if we want to bypass this, what we say, that capacitor, like if you are going to put this circuit breaker in a closed condition, for this we have used this bypass circuit breaker.
Yes.
Okay, if I just put 0 here, then it will be bypassed. Okay, and other than that, what it is, what this 10.9 is like, this is nothing but what we say it as. We say it as a partition insulator. Here, can you see this? There is something called as partition insulator.
Yes.
Okay. How we can identify there is a partition insulator is that I will come back. Okay. But what it does is like for each circuit breaker, there will be some partition insulator between them. Okay. There will be some partition between them. Okay. This is for the circuit breaker. And for VT, how we have to model? We have to just model it as a capacitance to ground.
Yes.
Okay, we have to model it as a capacitance to ground. I hope you can see this model, right? This is capacitance to ground.
Yes.
Can you see here? I have modeled it as a capacitance to ground.
Yes.
Yes. And other than that, what we have some disconnectors, right? This is one disconnector. Yes. Okay, if you go inside the disconnector, can you see this? I have modeled the same like the circuit breaker. The only difference is like this picofarad.
Yes.
And then the distance, the contact, what do you say that how much
long
contact size it has. Okay, the other part of the what do you say that for the disconnector. Okay, this is how we have to model the disconnector, circuit breaker, and VT. And other than that, what we have on earth switch, right?
Yes.
We have earth switch. How we have to model the earth switch?
Again, same as a circuit breaker.
Yes,
just
as a
a line?
circuit breaker, yes, we can model it as an, what we can model is like, we can model it as an capacitance to ground,
Ground.
or else if we, capacitance to ground, or else what we can do is like, we can just put surge impedance for that.
Yes.
Okay, surge impedance for that, and we can model it. Okay, and other than that, what we have, I hope we have only one current transformer. Current transformer can be modeled it as a surge impedance also.
Surge impedance.
Okay, surge impedance.
Yes. Yeah.
For this, where we have got data, we have got data from this point.
See this
There,
this particular sheet that you're showing. So it should apply to every GIS in that particular series which is written on the top. Is that right? Or is just for this installation? So
you are asking.
any GIS which is
Yes,
ELK type 3 420
420
420 kV,
kV. Yes,
it should
which
go to
has
everywhere.
yes, which has an insulation of what is
Yeah.
the bill level of 1425.
Yeah.
For that, we can use this.
Yes.
Okay,
Yes.
but depends on the GES type. What happens is like they might have use SP31 circuit breaker,
Yes.
SP3 circuit breaker. It differs from
We need to know that.
GS to GS.
Yes.
Okay, we have to get this information from the customer too. What is the type of circuit breaker they are going to use inside the
Yes.
inside the GS? Okay, that is how we have to get it from the customer. This data. Okay, I hope we have
Yes.
covered
Yes.
here things, positive things, which current transform, bus duct we have shown, right? How we have to model the bus duct? We have to just measure the total length of the bus
Yes.
duct, and then we have to put it as a surge impedance model. I
Yes.
hope Gokul might have explained this.
Yeah, we explain all these things in lightning example.
Lightning examples.
Apart
Okay,
from
okay.
that VFT diagram.
Yes, that is good. Then you have some basic information, some basic idea about how to measure this kind of things and all. Yes.
Yes. He explained it to me, and this GIS layout I have seen like 10 times.
Okay. Yes, it is good. It is good. Yes.
And not for the
then
EMT again, but just for everything. Yes.
just for that thing. Yes. Okay. Okay. Then you have got the information how to measure these things and all, right? How
Yes.
we have to measure and how we have to model, right? Okay. That is how I have modeled this complete substation. For 400 kV, I have modeled this complete substation. Okay, for complete substation. What is the information which we
This
need
is
to give here is,
yeah,
yes, tell.
this is the same diagram as a
Uh,
as a
we use
lightning
it
one.
for
Apart from
lightning one. Yes, the
apart
same we can use. Yes, tell me.
apart from that VFT thing, or is that not included in this one? Because
It
there
is
was
it is the same diagram which we have used for the
yes.
lightning purpose, lightning voltage studies. Okay, for lightning and VFTO, the model remains the same. The only thing which we want to change is like we have to change the disconnector model.
Yes, that's what I am asking. Yeah, only the
That
disconnector is
the
changed.
only
Apart from that,
disconnector model
everything is same.
will be the same. Yes.
Okay.
Other thing is like we don't need to model the what we say that we don't need to model the complete transmission line and all. Okay.
Yes.
The basic thing is like what we are going to what we are trying to do is like we are going to create a 1 per unit voltage on the on one side, and we are going to have a -1 per unit on the other side. Okay, so that what we have to do is like here we don't want to model the what we say that source as an with H by a ratio and all. Here we can just take an ideal source.
Yes.
Okay, ideal source is enough to model this. We also don't need to model the transmission line cables and all.
Yes.
Okay.
Another thing is I just recall from the last lightning one, because last time we modeled this 400 kV, and then we didn't go to the 220 kV part, right? We just modeled 400 kV and we sorted the either end, the further end going towards the substation and towards 220 kV. So it's not needed again the same thing for this as well, or do we need to?
No. We have studied different cases. We have studied for the 220 in other case.
Yeah. So the question is, if you are studying the 400 kV, right? So it depends how these two how close these two substation are, and then you neglect them, or you just neglect them. Like for example, this 400 kV GIS will be connected by say maybe 500 meter of cable, cables to 220 kV GIS. So even then you will exclude the 220 kV from this study or not?
No. For vffo, what generally happens is like this is
No,
the
not for the
voltage.
VFFO. I'm talking about just for the lightning example, for example.
Yes, lightning purpose, what we have to do is like we have to model the complete, what we say, that complete station, like 400 kV, we have to model 220 kV, we have to completely model in a particular file, and we have to see what is the surge which is transferring to the other part of the substation also.
But in that
You know,
example, we only model the up to the transformer,
we only
right?
model the transformer only, but what we have to do is like we have to completely model that other part
Yeah.
also.
Yes,
Other
that's
part
what.
also. Yes, we have to
Okay.
model completely the other part also. Then what we have to do is like we have to see what is the surge that is transferring to the other side that we have to
Yes.
see.
Okay. Okay.
Okay.
I got it.
Yes. Mm. Generally, the other information which we have to get it is like how the 220 kV side modeling has been there. Okay, if the 220 kV side which they have also they have if any transmission line, then there also we have to study this lightning impact.
Okay.
I hope that is clear for you.
Yes. I got it.
We have to model that, and then we have to perform a lighting study there, and we have to see how this impacts the insulation strength of the substation.
Exactly.
That we have to see. Yes, exactly. Yes. Okay. And I hope you don't know about the gas insulator. What is it? The gas line diagram also. You don't know about that. Yes.
No.
How I have modeled this gas line.
What is the gas line diagram?
Yes, I will tell you.
The diagram of the gas inside the these GIS.
Like that. Yes, I'll show you. There we from the other part which I have shown there, from there we can see what is the distance between the GAB, like that information we can
Yes.
take it from there, right? But what we can do, we want the arrangement of the devices, right? How this
Yes.
devices has been arranged and how we have to show, like that. For that, what we have to do is like we have to get the gas line diagram from them. Okay, this is how the gas line diagram looks.
Okay.
Okay, here can you see this? This is 1.5 breaker scheme.
Yes.
Okay, this is one breaker and this is one breaker and this is one breaker. Okay, this is generally an 1.5 breaker scheme. Here can you see this? There is some incomer from the cable
Yes.
and
That's correct.
transmission line. Yes, here you can see this. There is air subsets like that they have done. Yes, so it
Yes.
is cable incomer, it is a transmission line incomer, it is cable, and again it is transmission line. It goes on. Okay,
Yes.
like this. And I have said something like partition, right? I have said
Yes.
something like partition. Can you
Partition.
see there is a black line between the circuit
Yes.
breaker. It is a circuit breaker. It is a partition. If you see a black line, it is called a partition.
Yes.
Okay. What does it says is like if the circuit breaker has been damaged, what they can say, what they can do is like they can um, just take this part out and they can block these sides, block these two sides. Okay, and then they can operate the other part of the system without having this circuit breaker.
Yes.
Okay, I hope you can get that point. Okay, this
Yes.
is just a partition insulator. How we can know that? We can know that from the
Key.
key SLD diagrams. How it may be. Here, can you see this? This gray color indicates partition insulator.
Yes.
Okay, like this we can get all the informations like whether it is a disconnector, whether it is a circuit breaker, how they have modeled, like that information we can get it from here.
Yes.
Okay, from the key SLD. Okay, this is how your outline of the substation should look, should be modeled for the PSCAR model. Okay, this is how I have modeled here also in my PSCAR view.
Yes.
Okay, for the arrangement of equipments, I have took the information from the gas line diagram and I
Yes.
have modeled this. Okay, and other than that, what I have to do? Yes, then we will go to this uh, disconnector modeling. Okay, we will go to this disconnector modeling and we will see after completing this disconnector modeling, we will see how the cases have been formed, that we will see.
Okay.
Okay, Now I will go inside this disconnector modeling. Okay, just I have model it as a module. I will just double click and I will go inside. This is generally a disconnector model.
Mhm.
Okay. Yes. Shall we take some 5 minutes break? I will come back.
Yes, yes, please. Yes, yes.
I will just a 5 minutes break. I will
No
come back.
problem, mate. No
Yes.
problem.
Yes.
Cheers.
We will start correctly at 3:21. Okay.
Okay, okay.
Yes. Yes. Just a minute, we can start Himanshu.
No problem. No problem. Take your time, man.
My screen is visible, right?
Yes, yes, I can see it. Yes.
Yes, this is the what we say that this is the disconnector modeling, which we have modeled using the data which we have got from the customer, right?
That
I will
that
share.
tree diagram.
Yes, I will convert this into a double screen.
Yes. So
Okay, can you see? Can you get the view?
yes, yes, I can get. Yes, ma'am.
Okay, here we have R and we have capital R and C. Yes,
Yes. Yes.
capacitance we have. Okay,
Yes.
this is how I have modeled the model here also. Okay, what I have done, I have took the value of this resistance
Point.
capital R 0.5 and the value of capacitance 10 picofarad from here.
Yes.
Okay, and how this why we have modeled it as an
Variable.
what is it that variable resistance means
Yes.
what generally happens is like in this type what we are generally trying to do is like we are trying to create 1 per unit on the right side and 1 per unit minus 1 per unit on the left side,
Left
right?
side. Yes.
Okay, for that what we have done is like here can you see this for creating minus 1 per unit what I have done is like I have created a breaker here and I
Yes.
have created a DC source. Okay,
Yes.
DC
Current source.
voltage source I have put it
Oh,
here.
sorry,
Uh,
that's a voltage. Yes.
it is
Voltage.
an voltage source.
Yes.
Okay, I have created an voltage source and I have I'm going to insert a voltage here.
Yes.
Okay, how I have calculated this voltage?
That's 420
Uh,
divided by
yes, 420 divided by
root 3.
yes, 420 divided by root 3 we will be getting 242. Then
Yes.
we have to take the peak value, right? Peak
Yes.
value what it
Root
will
2.
be? It is 342 into root 2 we will get 342.
Yeah.
And then what we have to take is like we have to as he said we have to take some increase in voltage, right? Like for 5 percentage or 10 percentage that we have to take here. What I have done is like I have taken 1.1 one times, right? That is nothing but 10 percentage increment.
10.
What we get is like 377.22.
Yeah.
Okay, that is the voltage which I have created here. I am trying to inject it into the what you say that on the right side
Yeah.
of the disconnector. Okay, it is generally for creating minus 1 per unit. Okay, here I
Yes.
have, can you see this? I have given a minus sign here.
Minus sign. Yeah.
Okay, this is for creating a minus 1 per unit. Okay,
Yes.
and then what we have to do is like here we have 1 per unit.
Yes.
Okay, here we have 1 per unit. But what generally happens during a disconnector closing is that we have a huge resistance. What we say that we have a huge resistance.
Yeah.
Okay, before the disconnector starts closing.
Yes.
Okay, in order to model that huge resistance, for that we have that resistance will be decreasing as the disconnector comes closer and closer to the
Closer.
other side of the contact.
Yes.
Okay, for that what we have done is like we have modeled that part as a exponentially decaying part,
Yes.
exponentially decaying resistance to be more specific. Okay, we have modeled that as an exponentially decaying resistance. How we have modeled it? How we have modeled is like we have to use the values which is given in the data sheet from their side. Okay,
Okay.
can you see here they have given the data for that
Yeah. 10 to the power 12.
10 to the power of 12. Okay, this 10 to the power of 12 is the resistance which is there as an infinite source.
Infinite source.
Okay, infinite resistance that they have told it as 10 power 12.
Yeah.
Okay, the other part which we have used is like this is used for the what we say the decaying of the
Decaying
component.
part. Yes.
decaying path. Yes, for that what we have done, we have used the exponential path. Okay, and then what we have done is like I have put the same value there. Okay, for this or where it gets input is like it will be getting input from here.
Yes.
Okay, it will be getting input from here. Okay, here here if I go inside this part, I have modeled that. Yes,
Yes.
can you see here? This from here the input is going to all the three resistances.
Yes.
Okay, this is the exponential part which I have modeled. Okay,
Yes.
here you can see this. I have modeled it as an 10 power 12. Okay,
Yes.
this is an 10 power 12 and it is an coefficient component.
Yes.
Okay, and it is an coefficient component which I have modeled here. Okay,
How you
this
reach
how
that
I
coefficient component?
this how I have modeled.
How do
One
you
divided,
get that
yes,
component?
yes, 1 divided by the value which they have given there, right?
Ah, right.
Uh,
Yes.
yes, 0.6 into 10 power something they have
Yeah.
given there,
Yeah.
right?
Yeah.
10 power minus 9, right? If I put that value 10 power minus 9, if I put that value, what is the value which I will get? I have entered here.
Okay.
Okay. Then what it does is like now what we have done is like we have completed the exponential part. Okay,
Yes.
we have completed the exponential part. Okay, the other thing which we have to do is like at what time this what we say that this um, this resistance should start decreasing. That we have to say, right? That we
Yes.
have to say. Okay, that how we have done is like here we have been taking time from the simulation time. Here we have
Yes.
some, we might have told some simulation time, right?
Yes.
0.202. Okay, that is the time which will be the input for this complete component. Okay, and other than that, what we are doing is like we are taking the input as DSR. Okay, DSR.
Yeah.
Where this DSR comes from? Where this DSR comes from?
From the sheet.
This DSR is nothing but the time. Okay, the time at which we are going to uh, introduce this
Yes.
exponentially decaying component.
Yes.
Okay, we do need some time, right? At
Yes.
what time I have to introduce that? When my left side of the pot, like left side the one per unit pot. When my system is like one per unit, at the time I have to introduce my this exponential pot. Okay,
Yes.
I have done what is done is like I have gone mm, inside this ideal source.
Yes.
Okay, in this ideal source, what I have done is like I have created a ramp up time of 6.2 e power minus 5. Okay, then what we can say at this time, what it does is like your system will be attaining 1 per
Yes.
unit.
One per unit
Okay,
voltage. Yes.
at 1 per unit. Then what I have to do, I have to give the same time for this here also, right? For
Yes.
this closing disconnector also.
Yes.
Okay, for that what I have done, I have taken that time as a information, initial value,
Yes.
6.2 into e power minus 5.
Yes.
Okay, then what it does is like it will compare the input from here and here.
Yes.
Okay, this input will be staying as a constant one, which is 6.2 into e power minus 5. Okay, the other input which is going to come here is like the time which is running for the simulation. Okay, and then what happens is like if your time is, let us say it is initially it is 0.
Yes.
Okay, initially it is 0. Then what my comparator does is like it will compare these two values,
Yeah.
Then what I have done is like I have created a comparator where my level is I have put the output type as level. Okay, we have two types here. I have used the level type.
Level.
Okay, level type. Okay, and then for that I have to give the control, right? If I go
Yes.
inside this level, can you see this? I have given output when my A is greater than B.
B.
Here you can see, yes.
Yeah.
When my A is greater than B, then my output will be 1.
One.
Okay, then my output will be 1. Until what we say that until then my output will be 0.
Zero.
My output will be 0. So what happens is like generally this exponential part won't be coming into
Picture.
action. Yes, we won't be coming into picture. So when my time goes beyond this limit, 6.2 into e power 5, then what happens is like this time will be higher than this value. Then we will get a what do you say that? Then we will get an output. Then we will start getting the exponentially decaying resistance.
Yes.
Okay, this is how I have created this model. Okay, for this this resistance will be getting information from here. From there, it will be getting updated. This exponentially decaying part will be coming into action. Up to this point, you are clear?
Yeah, up to this point I am clear. What is that F junction doing in that D, in the just above the comparator? DSR. Yeah, this one, this another input. F,
This
F,
this
F.
this yes. Tell me yes.
Yeah, so the one side it's D, that's time, and then time is
Yes,
getting
that is
compared to the
time.
bottom.
And
What is this
again,
DSRCR? Yeah.
DSR is nothing but the 6.2 point e power minus 5.
All right, that you controlling from.
That I have got it as an input. Okay, we have to multiply with some t value, right? We have done we have taken value for this tau.
Yes.
Okay, we have calculated this tau, and then with tau only we have given the value here, right, for exponential component.
Yes.
Okay, in this we have other component, right?
T.
This t, this
Yes.
t, this is the one which tells you the decaying time.
Yes.
That is the time which we have used here.
Okay.
This
Okay.
will be the input. Like this, it will be decaying as the time goes on. Okay. There you can see, like when you put e power minus of higher value, it will get zero at some time. Zero at some time. Okay, that is how we have modeled here. Okay. And other than that, what I have to tell, I hope I have told everything. But other than that, what we have to do is like we have to inject we have to make the circuit breaker close at the same time, like this is happening, right? This 1 per unit minus 1 per unit should come at the same time, like this 1 per unit is coming into a picture, right?
Yes.
For that, what I have done is like I have given the same second, like 6.2 e power minus 5 for all the breakers.
Yes.
Okay, when this comes into action, this will also come into picture. Then at right side you will have 1 per unit, and the left side you might have minus 1 per unit. Okay, you will have minus 1 per unit. Then this two will be coming into picture, and then it will produce a stripe.
Yeah.
vffo generally. Okay, this is what generally happening inside this closing disconnector.
Yes.
Okay, the basic part which we have to understand is like the other one part is like whenever we take a case, whenever we are going to take a case, we have to take some reality kind of things. Okay,
Yes.
reality kind of things. Okay, this disconnector, no, there is the disconnector. This disconnector cannot be closed. This disconnector cannot be closed with a load current. Okay, that we should be very clear. Okay, this disconnector cannot be closed with a
Load current.
load current. Okay, then what we have to do is like we have to close this disconnector. We have to close this disconnector without by keeping all the other side as open. Okay, then only the current won't be passing, right? You got that point. For that only what I have did is like this disconnector will be closed first, then only your circuit breaker will be closed. I hope that point is clear for you.
Say again, when the down disconnector will be closed.
Yes, I will take a paint. The general thing is like here we have a disconnector, right? This disconnector will have one side 1 per unit, which we say it as AC, and which is 1 per unit. Okay, this is an AC port.
Yes.
Okay, the other side which we have is a DC port.
Yes.
That is how we have model. It is minus 1 per unit.
Yep.
Okay, this is how we have to take the scenarios. Okay, wherever this scenario is possible, we can create a case. Okay, for this, what we have to do is like the other thing which we have to keep it in mind is like this disconnector cannot be closed during this disconnector can be closed during only no load time. No load time.
Yes.
Okay, for that what we have to do is like, generally if we have a circuit breaker, generally we will have a circuit breaker in between the disconnector. Okay, we will have a circuit breaker in between the disconnector. Okay, generally we will have a circuit breaker in between the disconnector. Okay, what we have to do is like, this
Open the,
circuit breaker should be kept open.
yeah.
Okay, then only your load current will be there, will not be there. So that this when at the time we can we can close the circuit breaker. Sorry, we can close the disconnector and perform the studies. I hope that is clear.
When this circuit breaker will be closed, then if sorry open, right, and then if you close that disconnector, then ultimately there won't be any power flow in the system.
Any power flow. Then we have like we have got the, what we say that
Yes.
we have accepted the condition like it has closed during no load current
No
only.
load current.
Yes, yes. When after this closing, then if we close the circuit breaker, there will be a power flow. Until then, there
Yes.
won't be any power flow. Okay, this is how we are going to create a vffo.
Yes.
What we have here is like, in this side we have 1 per unit, and
Yep.
this side we have
Minus
minus
one.
1 per unit. Okay,
Yes.
as I said, whenever the
And
this
then when we
voltage
close
is
this connector, we will also close the circuit breaker.
no, no, no. In this vffo, we
No.
won't be closing this circuit breaker. We won't be closing this circuit breaker. That is what the information I'm going to tell you. We won't be
Okay.
closing the circuit breaker. This circuit breaker will be always be kept open.
So
Okay.
if you keep that circuit breaker open, how this fast transient is going to travel to another part of GIS?
Yes, that I will tell you. That I will tell you. Whenever they energize this pot, what happens is like, they won't be keeping this circuit breaker. What we say that they won't be keeping this circuit breaker as a open closed condition, as a closed condition. Okay, they will always keep this circuit breaker in a open condition only. Okay, whenever we are trying to close this disconnector. Okay, what is the concept is like, we have only trapped charges here,
Yes.
right? We have trapped charges. This trapped charges only we have modeled it as a -1 per unit.
Yes.
Okay, whenever we try to close this circuit breaker, what happens is like, due to this what is it that due to this open circuit here, what happens is like, there will be some traveling waves will be generated, right? After seeing one open contact here, what we have to do is like, we have to measure the voltage here. Okay, generally what we are doing is like, this much of voltage we are assuming like, this much of voltage will be generated on the other part of the GAS. That is our assumption. I
Okay.
hope now you got the point.
Yes. Yes. I got that point. Yes.
Whatever the thing which we are going to do is like, when we measure the voltage here, then we can get to the traveling voltage, traveling wave here, right? That voltage, what we assume is like, this is the amount of voltage which is going to be transferred into that other part of the GAS.
Yeah. So
Okay.
you are only focusing the simulation between the disconnector and circuit breaker. Is that right?
Circuit breaker, yes, yes.
Okay.
Where and all, yes, where and all we find a open circuit, there we have to measure a voltage, measure
Voltage.
the
Yes. I
voltage.
get that.
Okay. That is what we have done in this simulation also. The cases which we have done, also we have done the same. I will
Yes.
show the
I got it.
case. Okay, this is the case about. I hope I have taken about 6 cases here. Okay, I have taken about 6 cases here. What I have to do is like, the basic concept is like, one side I have to have a DC source, sorry, AC source, and other side I have to have a DC. Sorry, I will tell you again. In one part I have to have a AC source, and other side I have to have a DC source. That is the concept.
Yes.
Okay. Okay. Now what I have done is like, here I want to have one AC source now.
Yes.
Okay. For that AC source, what I have to do, I am just closing this disconnector. Okay, I have what you say that I have closed. The only concept is like, I want to have a AC source here.
Yep.
Okay, now I have a AC source on the right side here, this side. Right, I have a AC source in right side. Now what I have to do is like, in the other part I have a DC. DC component. What is it? That I have a DC voltage here. Right now, what I will do is like I will perform a closing disconnector operation here.
Yeah.
Okay, this disconnector will be performing a closing disconnector operation. Okay, at the time what happens is like in the source side I have 1 per unit of voltage. Can you see this in this graph? It is 1 per unit. Okay, it is 1 per unit. I have about 1 per unit on the AC side. Okay, this is source side. This is nothing but a source side.
Yes.
I hope it is clear.
Per unit.
Okay, and then what happens is like when my closing operation gets what is it comes into action, I have on the other side I have what I have minus 1 per unit. Can you see this? This voltage has suddenly dropped to
Yeah.
minus 1 per unit. Can you see this? This voltage has suddenly dropped to minus 1 per unit. How we can see this? I have shown here, right? This is on the other part of the disconnector.
Yes.
I will show it in the simulation. This is the closing disconnector. Okay,
Yeah.
in this closing disconnector, I have measured the voltage on the left side, which is an AC port,
AC
on the right side, which is an DC port. Okay, what I have said on the AC port, we should have 1 per unit, right?
per
On the
unit.
DC port, we should have minus 1 per
Minus 1
unit.
per unit.
Yes, that for that what we can do, I have taken the graph from the simulation, right? In the simulation, in the source side, I have 1 per unit.
Yeah.
In the source side, I have 1 per unit. Before I have performed the simulation. Okay, let us assume that if I have not performed any closing operation, this 1 per unit will go like this.
Okay.
It will be a straight line. It will be a straight line.
Yes.
Okay, now what I have done is like since I have performed the simulation, this is like there is a dip. Okay,
Yeah.
this is on the source side. Okay, source side I have 1 per unit. On the on the load side I have to have minus 1 per unit. Can you see this? I have about minus 1.15 per unit.
Yes.
Okay, this is how I have created the scenario. And then what happens is like you have to see the over voltage which is happening on the open end, right?
Yes.
In this, where is open end? Here, this circuit breaker is the open end.
Yes.
Can you see this? This is circuit breaker is the open end. Can you
Yes.
see the amount of over voltage which is developing? It is minus 2.215 per unit.
Yes.
Okay. If we have some other open end, there also we can see the what is it that we can see the over voltage. In this bus, I have a what is it that I have to measure the voltage at the bus also. This is an bus, right?
Yes.
This bus has an what is it? There will be some open end, right? At this open end, I have to measure the voltage. Can you see this? In this open end, I have measured the voltage,
Yes.
and I have plotted it also. Can you see this? The voltage which has developed inside the GS is 1.780. Like this, I have taken some other cases also. For transformer bay, I have taken some cases where the transformer is connected. For that, what I have to do, I have to measure the transformer 400 kV side voltage also. Can you see this? It has gone about 3 per unit. It has gone about 3 per unit after the action has been performed. Okay, this is due to the condition called here we have a long GAB. Okay,
Yes.
if you don't have any GAB, this won't be happening.
You don't get
Okay, this much voltage will be there.
Yes.
Okay, this is how I have performed the cases. I have performed for the transformer bay. I have performed the cases for the reactor bay. Okay, I have performed the cases for the reactor bay. And then other than that, what I have done is like I have also done cases for the 220 kV side
220
also.
kV GIS. Yes.
220 kV side GAS also. Like the same condition I have created, like here you can see this, I have created a 1 per unit and then to minus 1 per unit, I have created the same scenario, the same which I have explained now.
Yes.
Okay. What I will do is like I will share this file which we have used for this vffo simulation.
Okay. Yeah.
You can go through this file.
Yes.
Okay, completely go through this file, and if you have any doubts, kindly ask. I will. We can discuss about it.
Yes.
Just know if you have any doubts, whether you have any doubts.
No, I don't have any doubt. No,
Yes,
the modeling seems okay apart from the disconnector modeling. Of course, it's the same as before, but the disconnector is modeled in a detailed way.
Detailed way.
And I think to understand that, first I need to understand the theory in a greater way. Like how
Yes.
this disconnector operation works. But like you said here is like when you open the disconnector, before that you open the circuit breaker, and that's what you want to measure the voltage on open end to make sure
Yes,
that
circuit breaker won't be open. It will be kept open. It
yeah,
won't
kept
be
open.
going
Yeah,
into
yeah,
close.
yeah,
It will always be kept open. Yes,
kept
yes,
open. Yeah, and
yeah.
that's how you are trying to measure the voltage on open end that will appear on
Open
this.
end and the
Yeah.
other. What are the open ends I have? I have to measure the voltage.
Yes, yes, yes. Okay,
Okay.
okay. Yeah, I got that. I
Yes.
understand, these things in general, but not like in greater detail, like you are explaining, of course.
Yes, yes. That you can that confidence you can get when you try when you complete this modeling. When you try
Yes,
this modeling by yourself and complete it in a successful manner, then you can get that confidence.
yes, yes, yes.
Mm. You will get lot more what do you say, that lot of doubts when you try when you start modeling. When you have completed modeling, you will be in a much better confidence level.
Yes,
I'm sure. Yes.
hope so.
Yes. But this is somewhat a big project which I have got. The
It's
first
really big.
project,
Yeah,
it is.
a question on this.
Mm.
How much time it takes you to model this, just as a general? Because at some point, if I stay
Uh,
here
uh,
and if I get asked for example, a quotation, so to
uh,
gauge hours roughly, like how much time it will take you to model this full GIS?
It does. It also it generally depends on the size of the circuit breaker, size of the
No, this substation I'm
substation,
talking, like how long it
size
you.
of the substation, and how fastly the person who is modeling, that also depends.
But
Okay,
generally, you will
for
take at least 4 weeks, right, to
yes,
model
I will take
easily,
generally 4 weeks. Yes,
4 to 5
yes,
weeks
okay,
easily.
yes, 4 weeks. Yes, it will generally take 4 to 5 weeks to
Yeah.
complete a big substation.
Yes, big substation like this. Yes.
Big substation. Yes, yes.
Yeah. No,
Other than that, we want all the inputs
of
to
course,
be valid.
that is
Yes,
a big battle always.
yes, yes. Somebody won't understanding what was the input we are asking from them,
No, no,
like that.
nobody understand. They just send you a
Uh, uh,
specification and then they ask you where is my report.
where is my report? That is what they used to ask.
It happens
Then
everywhere.
it happens everywhere. Yes, yes,
Yeah.
yes, mate. What I will do is like I will share this file with you.
Yes,
Okay,
that would be
I
lovely.
will share this PSCAT file. You can completely go through this, how I have modeled and how I have uh, taken the scenarios, different scenarios. Okay,
Yes,
that you can see. And I have also plotted, just see the scenarios and how I have created the scenarios. Then if you want, you can run the simulation and you can see the graph. Okay,
yes, yes.
that I will share all the cases which I have done with you.
What was
Okay,
the Seagrave brochure number that you have?
that also I
That's
will share.
519. No, no, it's
That
fine.
also I will share.
I may have that.
Okay, okay.
It's
It
519. Is that
is.
right?
No, mate, I haven't seen this. Yes, it is 519.
Okay.
It is
Yes, yes.
519.
Okay.
Okay.
I
Other
have
than
that.
that, if you want to learn something more about how I have modeled the disconnector, I will share this too. This is one paper written by, it is an IEEE paper which is done by somebody called Vinod Kumar. Okay, that I will share it with you. Okay.
Okay, that would be great.
Yes,
Yes.
yes. Other things what I have to share. I hope that is enough. I hope that the insulation, this I will share.
Yeah.
You got this input, right? You
Yeah,
have
I got
also.
this. I got this
Uh,
anyway. Yes.
then what I will do is like I will share these two papers.
Okay.
See, and this two I will share. Other
Okay.
than that, I will share this also. This is a general information how the GIS looks like for the different types of feeder configurations, like bus bar configurations.
Yeah.
That I will share.
It is a
Okay.
lot of study.
Yes, it is a lot of study. Yes.
Yeah.
There they have designed the different types of voltage levels like 363 kV, like 245 kV. They have designed all those type of things.
Yes. Yes.
Okay, this will be useful to have
Yes.
a
I
go
am.
through.
I am aware of the structures and I am
Uh,
aware of the fact like how it looks, but not like the single line diagram right
things
beside to
like
it. When,
okay,
because I never done any job like that, so I never cared to
okay. They
to
got
look
it,
into
got it.
that. Yes.
Yes, yes. I will share all these things. Mate. Yes.
Yeah. Earthing engineer is pretty much like a a labor on like construction site. You need to cover yourself in mud and soil. That's how it works.
Okay, okay. I haven't gone to any site. Then if I go for any site, then I have to I will
No,
give
no.
you
I
say.
mean work wise as well. Like when you do the EMT simulation, you have nothing to do with the field, right? You're not going there to see anything, right? Unless
Yes,
you are
yes.
like a utility engineer and going like for a like witness testing or something. But like
Yes,
in
yes.
my case, like I need to go first for the soil measurement, and then a soil measurement could be like anywhere in the locality.
Uh-huh.
Like it can be a farm field, or you need to cross the drain, and even it's raining, or you just don't care. And same for the substation, like so
Substation. Yes,
yeah,
also. Okay. Yes,
yeah.
yes, 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 mate.
Okay.
Yes, that's the part which I have planned today. I hope Gokul, if you are available.
Yeah, yeah. Yes, yes, Venkat, I'm available. I can
Yes.
take care. Yeah.
Himanshu, from here, Gokul will take you some what do you say that some ferroresonance cases.
Okay.
He will let you through some ferroresonance cases, like basic things, and he will also explain how we have arrived for the some cases that he will explain. Like,
Okay.
okay, okay. Kindly work on this. You can
I
get
will do. I will
yes,
definitely.
you will get lot of doubts on this at the time. Just a message in WhatsApp. We will be we will clarify your doubts. Okay.
Yes. Yes. I will do. I will do.
Yes. Yes. Okay. Gokulji, Gokul,
Yeah,
you
yeah.
can.
Fine.
Yes.
Okay, Venkat. Yeah, thank you. So Himanshu, so we are going to talk about what is ferroresonance, like what is the basic theory behind ferroresonance, and how that is modeled in PSCAD, and what are the cases to be considered,
Okay.
and like and what are the cases you have to generally you have to take if you going to simulate a ferroresonance cases. So
Yes.
I'll just share my screen. I'll just
Yes.
show the SLD. Like since you're aware of the SLD, I can uh, just a basic on this.
Yes.
So this is our SLD, right? Like we have shared this also. This is one of the
Yes.
transformer.
Yeah.
And basically, what is ferroresonance? Like the ferroresonance is an non-linear inductance. If your system has a non-linear inductance, and the interaction between your non-linear inductance and your system parameters.
Yeah.
So the interactions between that is basically a ferroresonance, and that occurs some oscillations, and that may give some over voltage. So that is basic thing of ferroresonance, right?
Yes.
Yeah. So non-linear inductance is the inductance which is dependent on the current. Like if I change the current, then the inductance will change. Like that is
Yeah.
non-linear inductance, dependent on current. So since a non-linear inductance or the transformer is a non-linear inductance, and in a system, like there are different types of a reactor is also a kind of non-linear inductance,
Yes.
a transformer and a VT. Like in your system, you will have a VT, right? Voltage
Yes.
transformer.
Yes.
So
Yes.
that is also kind of
Gokul. For that,
yes,
what we
yes,
can say is like we have ferro in the name of resonance, like ferro resonance. We have in
mm,
between there is something called as ferro, right? Ferro means what I think is like it is generally where and all we have a ferromagnetic material. There we will
mm,
be seeing this ferro resonance.
yeah,
In transformer there will be a ferromagnetic material. So there we used to do generally see the ferro resonance there. That is what from my side.
yes, correct. So transformers and VT. Like so, the cases which you are going to perform, and the first thing you have to look on your system, and your system will have a VT, and if your system is a transformer, then you can simulate for ferroresonance. And there are some considerations to be done while doing in PSCAD. So we can just see the basic model and the cases which we have created for this system, for this particular system, for this SLD. So I'll just
VT and
show you that.
transformer will be everywhere, right?
Yeah, will be everywhere, and yeah, based on your system, you have to do the configuration, like the cases.
Yes.
Yeah, I'll just show you that. Uh, yes. So this is the cases which we have arrived. Basic cases are the energizing and de-energization transformer. Like that is the basic cases. like energizing and de-energizing of transformer.
Yes.
So what generally we used to do is while energizing a transformer, I'll just show you the circuit breaker. Like one of the cases I can take,
Yes.
and new case, not new case, longest path. So this is now case number 2. Like this is the overall SLD. Like can you see the overall SLD?
Yes, you can see it.
Yeah. So like I just zoom it and I'll show the each and every individual component. Like starting from source, this is a
Yeah.
source,
Yes.
and then this is a cable,
Yeah.
and then this is a transformer.
Transformer.
And
Yes.
I have modeled a separate module,
Yeah.
which is I just show you that. So from the transformer circuit breaker, I have modeled all the component. Like I'll just show you that too. So this is from RAF Super, right? So this is
Yes.
from the cable.
Yes.
So and this is the transformers. This is a transformer, right?
Yes.
So this is a transformer, and a transformer circuit breaker is over here.
Yes.
Yes.
Disconnecting.
So a transformer circuit breaker is over here. So from here, like from a transformer circuit breaker, I have a CT, I
Yeah.
have a disconnector switch, I have a earth switch and everything. Like from the transformer circuit breaker,
Circuit breaker.
all the all the components you have to model a nominal pi method. So this is a nominal pi method, which is one type of a method to simulate. Like we will use an frequency dependent method, right?
Yes.
For OHL.
Yes.
So similarly, there is an method like it's an
Bisection.
yeah, it's an pi section. Like it's an single frequency method.
Yes.
Like this is not a frequency dependent method.
Yes.
So there is a nominal T method and nominally pi method. Like we have used nominally pi method, and from the circuit break
Breaker.
from the transformer circuit breaker, all the components have been modeled as an nominal pi method.
Yes.
So I'll just open it up. First, we can discuss about the modeling, then we can go for the cases.
Yes.
So this is if just double click it, you will get this dialog box.
Yes.
So the title name, like you can give any name you want. Like it doesn't have any meaning on that. Like you can give any name, and the impedance admittance data, like it has different types of data methods you can give. Like
Yes.
in we have seen, right, like in FFO we
Surge.
have given a surge impedance.
Yes.
So something like that, but that is different. That is based on method. But here also there are a lot of method like R and X and XC, like inductive capacitor, inductive reactance and capacitive reactance in per unit in ohms, and just RXB in per unit. And if you have a surge impedance, then you can use it. So for time being, we are going to use this ohms because we have this value with us. We have this value with us in ohms. Like I'll just show you that. So 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 so
Yes.
so you got this data, right?
Yes.
This one of the data, like even Venkat also like tried to said how to take these values. Even in FFO we did the same thing, right?
Yes.
We took some values here. Even TRB are going to took the same value from like this is one of the important like data you should get. So here, okay, first step we are going to model the CT, the current transformer, because after breaker there is a CT. So what I'm going to do is I'm going to check here where is current transformer. So here the current transformer is, and then we have the inductance and like Henry, and we have the capacitance to it.
Yeah.
So we have the capacitance, we have the inductance. So like what they are trying to say is see bus duct below.
Yeah.
Like so there is a component bus duct.
No, it was just below that.
Yeah, here is exactly, yes. So here they have given what is the capacitance width and what is the inductance. Like this bus duct capacitance and the inductance is same for the current transformer also. So you can take the L value and you can take the C value, which is picofarad per meter. Like it's per meter, right? So what you have to do is you should know what is the you should know what is the like length of it. So
Yes.
like Venkat, I've shown you some AutoCAD file, right? Like
Yes.
there you can measure from the breaker to from the breaker to current transformer, what is the length.
Yes.
So and then you have to give it in here like line length, which is
Yes.
0.862 meter.
Yeah.
Then this is nominal method, and then this is the rated line rated frequency is 50 hertz,
Yeah.
and we are going to estimate it. Like we are going to estimate it. The software is going to do that.
Yes.
It is going to estimate it.
Yes.
Yeah. So the next page, like no, now you know how to take this value, right? Like
Yes. Yes. From the AutoCAD.
0.862 from the AutoCAD file. Like you should have to you should get that file from the customer.
Yeah. Yeah.
And then this is 50 hertz, like you can get it from the system frequency. Then
Yes.
the enter zero sequence or estimate, you have to give estimate.
Estimate.
Next, because I have the L and C values with me, which is in ohms, I'm
Yeah.
going to take this value.
Yeah.
If for example, if I have surge impedance, if I'm going to take the surge impedance, then I can go for this value.
Yes.
Or if you have a per unit value, you can go to this value. So based on the data availability, you have to choose.
Yes.
So I have this value, so I can easily go with that, and I can easily do that. So this is you can just give 1.5, like because this is the thing we are going to like calculate. So the positive sequence resistance, you can give the minimum value, like 0.0001, like it is minimum value.
Yeah.
And the next two things you are going to calculate:
Yes.
the capacitive reactance and the inductive reactance.
Yeah.
So Excel, like you know
Fine.
what is the formula for Excel is
Yes.
2 pi fl. So you know what is the frequency, you know what is the L, like
Inductive.
L into 0.862, which is the meter.
Yes.
So that you should not forget.
Yes.
Then if you just then you'll convert into mega ohms, you'll get 52.57. Like if you get like, correctly, if you like 57.24,
Yeah.
you'll get 57.17. So that is the value I've taken. But since in PSCAD the units are important, so they will ask in a particular unit, so you have to give in that unit only.
Only. Yes.
So you don't try to change it unit, because
Yes.
it may we may end up with some issues. So don't try to change the unit. Like if like bare minimum, it will have some units, and try to convert the values which you got to the unit which is PSCAD asking, and you can just like input just give the value.
Yes.
Then the XC is easy.
Yeah.
Yeah. Then the inductive reactance and capacitive reactance.
Yeah.
So X is equal to 1 pi 2 pi FL. So
Fine.
if you got like 6.63 into ohms,
Yeah.
which is 10 into 10 power minus 5.
Yeah.
The same thing I have given, like 0.0, like 6.6 in, if you convert to ohm per meter, then you can give it 0.000, something like that.
Yeah.
So this is how you have to calculate for all the disconnector. We used to calculate from the that file itself.
You can also give me the file. Actually, I just checked. I don't have that brochure, like the ELK where you are getting these values. Henry
Fine.
and
Yeah, yeah.
I.
I can give you that file. Like
Okay.
just a minute. I'll just connect the charger.
Okay.
Give me just 2 minutes.
No problem. No problem.
Fine. Okay.
Yes. Yes.
Yeah. Okay. I will share this file. Like so, you're talking about this file, right?
Yes. Yes. This only. Yes.
So so today I will put this in our WhatsApp group.
Okay, that would be good.
So I will share this file. So you can take all those values, like all those values I have taken from here. Like for a disconnector,
Yes.
same, they are saying like see bus duct below.
Yeah.
So that same value you can take from the bus duct.
Yes. Yes.
Yeah. So and the one important thing is like the length, the line length will change for the
Yeah.
disconnector, because from
Yes.
CT to disconnector line length is 1.2745 meter.
Yeah. Yeah. That will come from AutoCAD again.
Yeah, that will come from AutoCAD. Like this is our model
Yeah.
for the bus stick for the CT. Like the same value you can take,
Yeah.
because it's
Just a different Henry and just a different capacitance, different length. Yes.
yeah. So you have to calculate. But the thing is, where you have to take is like you have to take uh, from the transformer circuit breaker.
Yes.
I have another modeling which is available in PSCAD itself. I'll show that. Like I can give you the basic difference between our modeling to that modeling.
Okay.
So our that PSCAD modeling like it's slightly different, but I'll let you know that like why they have done it and what is the disadvantage of that.
Okay.
So this is the basic thing. Like from the transformer breaker, you have to take it,
Yes.
because I'm going to energize this. If I'm
Yes.
going to energize this, then I will like do the operation on the breaker.
Yeah.
So from the breaker, from the transformer breaker, you have to consider all these CTs and disconnector,
Yes.
even bus duct, all the components. So these components will have a capacitance, right?
Yes.
And the transformer is a non-linear inductance, as I said. So there will be some like interactions between that, and there will be some oscillations, and due to those oscillations, there will be some over voltage.
Yes.
And we are going to check what is going to happen with the door voltage, or what is the maximum voltage that occurs, or if there are any oscillations is in my system.
Yes.
For that, we are going to simulate some cases.
Yes.
So there are some different types of cases. And for that, we are going to simulate that. I'll just show you those cases. So first case is I'm going to just energize the transformer, which is 500 MVA, those transformers.
Yeah.
With all circuit breakers, poles are closed at
Yeah.
0.3 seconds.
Okay.
So ferroresonance, like the basic part of ferroresonance is the circuit breakers, whether all the poles are closed, or only one pole are closed, or only two poles are closed.
Okay.
So that is the difference between each cases.
Okay.
Like if you ask me what is the difference between case 1 and case 2,
Yeah.
just read the last line.
Circuit
Circuit
breakers, all
breaker all
poles
poles
closed.
are closed,
Yeah.
but circuit breaker one
Y
pole
pole.
is
Y pole
closed,
closed. Yeah.
and other two poles are in open condition.
Yeah.
So that is the difference between the case 1 and case 2.
Yes.
And then there is another basic difference also we have to do. So here we have three transformers, right?
Yes.
Transformer G3, T3, T1, and T2. Like out of three transformers, we have to consider which is the shortest path from the breaker.
Okay. Okay.
You have to take the, if for example, T3 is the shortest path from the breaker.
Yes.
Say example, this T3 is, so the distance between the circuit breaker to here, like let us assume like 900 meter, like I'm just assuming it.
Yes.
Then for the T2, it's again 950 meter,
Yes.
and for the T1 it's again 950 meter.
Yes.
So if you have a system something like this,
Yeah.
what you have to do is you have to consider two cases. The first case is the longest path,
Yes.
which is 950. You can take any one of this.
Either of them. Yeah. And
Yeah,
one is
either of
shortest path.
them. Yeah, just the longest path. The second one is shortest path.
Yes.
For the longest path, you have to do cases like energizing the transformer and de-energizing the transformer
Yes.
with the circuit breaker poles closing and opening.
Yes.
For the shortest path also, you have to do two different cases, which is energizing and de-energizing the transformer with the circuit breaker poles open or closed.
Yes.
So you have so do you have any doubts up to this, like how
No.
to yeah. So the main thing is you have to take two cases. And how do you know this 900 meter? By having the AutoCAD file.
AutoCAD file, yes, of course.
So the AutoCAD file plays a very important role here. So you have to get it.
Yes.
So then you have to get that AutoCAD file, and you have to comment on which transformer has the longest path and which transformer has the shortest path.
Shortest path.
So longest path, if you take if you take a longest path, then there will be two cases.
Yeah.
One is energization
Yeah.
and de-energization.
Would you
Similarly,
would you do this ferroresonance just for the high voltage or just any voltage?
any voltage we can do it.
No, well,
Like
I mean, you do only for it, or it's like recommended only for high voltage?
it's not recommended for, like, if you have a transformer and if you have a transformer in your system, and bare minimum you have to do the ferroresonance. Sometimes the clients may ask,
Where else you
they
do this in ETAP?
ETAP we can't do it
Okay,
because ETAP is not the right tool for ferroresonance. Like
okay,
EMTP tool is the right tool.
okay.
Even I read in one of the thesis, like they have done the ferroresonance ATP, which you have shown, right?
Yeah, yeah, yeah.
ATP. Yeah, they have done in that also. Like EMTP is the right tool for that.
Okay, either
So
ATP, either this EMTP-RV or the PSCAD.
yeah, exactly. So even sometimes some clients may ask you to do the ferro resonance also.
You can't do that in other software like Dick Silent or PSAC.
Uh, no, PSSE and ETAB you can't do it.
Okay.
So yeah, but PSCAD is the right tool because it will be kind of user friendly for you.
Yes.
Yeah, so the basic path is you have to get the values from the AutoCAD, and you have to take two cases, which is longest path and shortest path.
Yes.
So now we can talk about the cases. So I have taken three cases, right? Like for energizing, I have took three cases.
Yes.
So one is all the three poles are closed at 0.3 seconds.
Yes.
All the three poles are closed at 0.3 seconds. The second one is one pole is closed at 0.3 seconds and other two poles is open condition.
Yes.
Like they are going to trying to energize a transformer, but due to some reasons, only one pole is closed. The remaining two poles are open. And the third case is two poles are closed. Like both the poles are closed, but only one pole is not closed. It's an open condition. This is for the energizing the transformer.
Transformer.
So similarly for de-energizing the transformer, there are other three cases, the same cases. Like circuit breaker is opened now because we have to de-energize it, right?
When you are
So
talking about this one pole thing, would you do that in real world, or you don't do it
um,
in real world?
yes, but in simulation we can do it, but real world there are
No, no,
some
just asking the like reason behind it, like other thing, we are doing like with a logic that somebody will end up doing these in the field. So
mhm.
my question is like, would you close just one breaker in the field or not?
Well, if you have a single pole operation, then you can do it. Like
Okay,
if you have a single pole operation, you can do it, but wantedly they don't do it
okay, okay.
because it
But
like
we
you
are
know
just
that, like,
trying to estimate the possibilities. Yes.
yes, because bare minimum if you close only the single pole, then like there will be some oscillations and everything.
Yeah.
So
Yeah.
they don't do that.
Yes. Yes.
So yeah, for the de-energization, the transformer, the circuit breaker should open, right? Because we are going to de-energize it. So similarly, the three cases, which is all the circuit breaker are open at 0.3. Only one pole is open at 0.3, and the other two poles are in contact. Next, the third one is two poles is open and one pole is in closed condition. So this is for shortest length. Case 1, case 3. From case 1 to case 6 is for shortest length. From case 7 to case 12, it's for longest path. So I have took two path, which is shortest path and longest path. Each I have each condition of 6 cases, and which is energizing and de-energizing of the transformer.
Yes. Yes.
So do you have any doubts on this cases, how to form
No.
this?
Not at all.
Yeah. Super. So this is important. Like this is important. So for like up to this, we are going to only talk about transformer. We will be talking about VT also, and how to model the VT, because modeling a VT for for ferro resonance is quite tricky.
Okay.
But simple thing. We can check it. We can check it.
Okay.
So I'll just show you the first case. So this is the first case. I'm sorry. No, yeah, this is the first case.
Yes.
So from source, from cable,
Yeah.
I'm going to take this. So this is the breaker. So like this is the breaker. So I'm going to, because this is the transformer breaker.
Yeah.
So I have to consider this only. I should not consider this breakers or the source side breaker.
Yes.
I have to consider the transformer side breaker. So that is important. That is important. So look at the time fault logic.
Thank you.
It's open because this is an energizing case. So like initial state is open, like at 0.3 second it will close.
Yes.
So the second phase also, it's at 0.3 seconds it will going to close, and the third case also at 0.3 seconds is going to get closed. So here there is no issue, like we are going to just close all the three breaker
Great.
and we are going to study the results. That's it. Like there is no I'm not trying to say that only one phase is closed and other two is open.
And where
The
we are
first
measuring
is,
the voltage?
yeah, here
Okay.
on the Albera, on the HV, on the 400 kV bus,
Yes.
on the transformer HV side and LV side. Like you have to show this 2 kV also, this 2 voltage.
Okay.
So I'll always recommend to show V220 also, like the 220 kV side voltage also. So can we go to second case so we can check the
Yes. Yes.
difference?
Yes.
Yeah. So this is second case, like case 2. So so the breaker one, see the breaker one is open, but it's going to close at 10 seconds, which is this is not going to close.
Yes.
So the second pole is going
Great.
to close at 0.3 seconds,
Yeah.
and the third pole is going to close at 10
Not.
seconds, which is not going to close.
Yes.
So which is only one pole is closed and the other two poles are stuck. It is not going to close.
Yes.
So we are going to see what is the over voltage, or if ferro resonance occurred or not.
Yes.
I'll try to just run this case. In one or two cases, we can just run and check it. Have the plot also. I can check. I can show you that also.
Yes. Yes. Can you also give me one of these files, just one of these
Yeah,
for my
yeah, yes,
reference as a
yes,
library?
yes, of course. I will send this. I will send this. Here I don't have any surgeries, so I can just send this. No issues on that.
Yeah. Yeah. Not just to keep as a reference, like how you do.
Yeah, yeah, fine, not issue. So you can check this.
Yes.
So there is no oscillations, right? It's just a normal sine wave. Like that, you can't find any abnormal oscillations, right?
Yes, but the magnitude are different.
Yeah, that's because of switching. This is not
Okay.
because of ferro. This is because of switching.
Yes.
The
Yes.
ferro means you can see the waveform itself. You can
Zigzag.
see it.
Yes. Yes.
Yeah, so I'll show you that in PSCAD example file. There is a case. I will explain that as well.
Okay.
There you can see the difference.
Okay.
So, but here in our case, there is no ferro resonance.
Yes.
We can just conclude that this voltage is because of switching. Like you should not confuse with that.
Yes.
This 465 is because of switching,
Switching.
but the other voltage is because it's because there is no oscillations, and we can conclude that there is no ferro resonance occurred in my system.
Yes.
So based on the system parameters,
Yes.
if the system parameters like if different, then there are chances that it may
Occur.
gives, yeah, it may ferro resonance may occur.
Yes.
So I'll just open the third case. Yeah. So this is longest path. I'm going to just open the third case.
Yeah.
Yeah. So it's again the same thing, but the only difference you can get it by just looking by opening this breaker. So it's opened at 0.3 seconds. It's good. Next is opened at 0.3 seconds, and the third one is not going to open. Like it's opened at 10 seconds. So technically this pole is not open. Like only two poles is
Yeah.
open, and
Yeah.
we are going to just simulate that, and we are going to check whether what's happened. So
Okay.
that these cases are energizing the transformer. The
Yeah.
same three cases you have to repeat for a de-energization cases. I'll just show you how to just do that. It's just simple, same thing. Like
Close
I
and
can
open and close.
yes, exactly. Like no, the we modified. Okay, yeah. So the only difference is the first one is no initial stage should be closed.
Yes.
So the initial state should be closed, and at the 0.3 seconds you're going to open. Like this breaker is not going to open.
Yes.
Like I can show you this breaker. Yeah, this breaker. The initial condition is closed because this is a de-energization case,
Yes.
and this is normally closed, and I'm going to open at 0.3 seconds.
Yes.
So you do you have any doubt up to this? Like just a simple thing, but
No.
yeah, but the issue is you have to frame your cases based on the shortest path and longest
Shortest
path.
look.
So this is important. And the other thing is from this generator circuit breaker, you have to know what all components are there, and you have to model those components as a nominal pi method with the measured length of it. So that is again an important thing in ferroresonance. So up to this we are talking about the how to say, we are talked about the transformer cases. But
Yes.
even VT is also nonlinear inductance. Even that may results in ferroresonance.
Yes.
So we have to consider those voltage transformer also, and we have to simulate that.
Yes.
So modeling a VT is different in PSCAD,
Okay.
because for ferroresonance we should model for VFFO or FFO, we will model just as a capacitor,
Yeah.
or just capacitor we used to model it.
Yes.
But in ferroresonance, that is how not should be modeled. Like it should not be modeled something like that. It should be modeled with the characteristics. I'll just open one of the cases. I'll just show you that. So yeah, so this is one of the case. Like I'm going to energize this VT. Same
Yes.
same case. I'm going to energize this VT. Like this is line VT.
Yeah.
So I'm going to energize this VT. So if you just go into VT, you can see this is the modeling should be used.
Okay.
This is a transformer, a single phase transformer, single
Yeah.
phase two winding transformer.
Yeah.
And one important thing, uh, for modeling this transformer, for the normal case,
Yeah.
for the normal case, uh, for sorry, I'll show this. For modeling this transformer, for the VT, the ideal transformer model should be, yes, like this should be in a saturation model.
Yes.
You should not model as an unsaturated. Like you should model as a saturable transformer.
Yeah.
Yeah. So, so I'll show you how to take these values. So I'll just open one of the. Uh, just a minute. Just open it.
Yes.
I'll just open it. Cables. Okay. Um. Just a minute. I'm taking the VT, searching for it. Voltage transformer. Hmm. Yeah. Uh, can you see my screen, Himanshu?
Yes, yes, I can see it.
Yeah. So this is a voltage transformer data sheet, like the same data sheet,
Yes.
but this isn't like voltage transformers data sheet. Like I'll show you this portion.
Yeah.
Here they will give you some basic things, like what is the frequency, what is the bill and everything. Like we need some basic things here. I'll just show you that. The rated voltage is 420. Let it be.
Yes.
So here the number of secondaries. The first one, the first winding you can give 400 bar root 3, and the second winding is 0.11 bar root 3. The same thing I have given here, which is winding voltage 400 bar root 3 is 231,
Yeah.
and 11 kV 0.11 kV bar root 3 is 0.0635.
Yes.
So you have to give the values here. The next thing is configuration. Same data sheet.
Yeah.
Like here they will tell you what is the old time. Okay. Type, or is the rated frequency, or is the old time. Yeah, here the rated output, the rated output is 50 VA.
Yeah.
So the same thing I have taken, I have take as a transformer MVS 50 VA,
Yeah.
and the base operation frequency 50 Hertz. And these things you have to get it from the transformer. I mean, the voltage like the client. There will be some VI characteristics.
Yes. Yes.
So the VI characteristics for the voltage transformer, you have to get it from them, and you have to give the saturation.
Saturation.
So you have to give the saturation to this.
Yes.
So the data for the VT is from the data sheet. You can take these values like 50 VA, 50 Hertz, and what is the winding voltage, and
Yes.
the remaining thing you have to get it from the VI characteristics of the VT.
Yes.
So the same thing, like this is single phase transformer. The same thing I just copied it and I'm going to place it, because so there will be three windings. So the same
Yes.
thing I've just copied it and I pasted it over here.
Yes.
And this is how you have to do for a VT case. But for this case, there is no need to separately model a VT. You can just model a voltage transformer, something like this, a normal pi method. But when you're going to like feel, or when you're going to study the interaction only with the VT, then you have to model a VT, something like this.
Yes.
So the next thing is the earth switch. Like this is a normal. This thing you have to model with the capacitance, and again this disconnector you have to model with an grading capacitance.
Understand. Yeah.
This is the grading capacitance. The grading capacitance means if there is a disconnector and between two contactors, two contacts, there will be some service some capacitance, right? That's an inevitable. So that is grading capacitance. So you have to model that as well. I'll open another yeah. So you have to model the grading capacitance and the stray capacitance when you're going to talk about only on VT.
Yes.
But while you're going to talk about voltage transfer, like sorry, power transformer, then this is the rule.
Yes.
Any doubts up to this, Himanshu?
No. No.
Yeah. So yeah. And here, what I'm going to do is I'm going to energize this VT, this line side VT. So this
Yes.
disconnector will be closed position.
Yeah.
So only between this I'm going to measure.
Yeah.
So only the because here there will be no voltage, like, or here there will be no voltage, or here there will be no voltage.
How you are energizing this VT then?
Yeah. So
Or from the
this
top?
N2.
Yes. Yes.
Yes, exactly. Like I'll show that. Um, so here, can you see it?
Yes.
So at 0.3, I'm going to just switch on this. That's it.
Yes.
But but I'm not going to perform any cases like this, which is a single pole and two
Yeah,
poles
yeah,
open,
yeah.
yeah, something like that. I'm not going to perform anything like that.
Yes.
I'm going to just give a command that at 0.3 I'm going to open this and I'm going to energize the VT.
Yes.
So yeah, and then you can perform, or you have to measure the voltage at here. I'll just simulate this. I'll just show you how the plot look like.
Yes.
Okay. This is the waveform we are getting. Sorry. This is the waveform we are getting. And by just looking this, we can say there is no oscillations. Like there is no
Yeah.
oscillations takes place.
Yes.
So we can conclude that there is no ferroresonance occurred in my system. If I just charge my VT, sorry, yeah, the charging my VT line VT. So there are some different cases for this. I'll just show you that. So this is where it is. Yeah. So this is where we are talking about this
Yes.
VT.
Yeah.
Sorry. So this is again from this is again from cable. Also, you can perform a cases.
Yes.
Just just a minute.
Yes.
Just close my window. So two cases you can perform. One is by energizing the
Cable.
line VT,
Yeah.
yeah, like cable VT, and the second one is line VT.
Line bit.
And then you're going to check the voltage over here. What is
Yes.
the over voltage, or what is the voltage I'm going to get it?
Yeah.
Only de-energizing case, there is no de-energizing case. Only energizing case.
Yes.
Okay. So these are the basic cases you have to do. We have if you like if your client asks for ferroresonance.
Yes.
Uh, uh, any doubts up to this, Himanshu?
No. 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 Not at all.
So since ferroresonance is just a simple thing,
Yeah.
sometimes the client will ask you like to perform a ferroresonance. Then you have to do something like this.
Yeah.
I'll show you how
Yes.
PSCAD will do it.
Okay.
I'll just open one of the cases. I can just open it. Paragraphs. PSCAD modeling. Ferro. CVT for ferro. Cable. Here it is. Here it is. So I'll share this also. Not an issue. I'll just share you this. Here they will give some cookbook. Like here they will
Yeah. I
give some.
got some. Yeah. Not very
Yeah.
ferro resonance, but I had some. Yeah.
Kindly check that. Check that. You'll
Okay.
get some good understanding on it.
Yes. I will.
I'll tell you what is the difference between our modeling and like the PSCAD modeling.
Yes.
Like what we used to do is we used to take the circuit breaker, uh, uh, the transformer circuit breaker,
Yeah.
but they have took the source side circuit breaker.
Okay. Yeah. Line breaker. Yes.
So if, for example, if you're going to perform energization of this transformer,
Yeah.
you will first energize this transmission line,
Yes.
then you will energize this power
Trans.
transformer.
Yes.
But here what they are trying to do is they are going to energize both of them.
Together. Yeah.
So that is a remote end thing, right? Like it will not
Yes.
happen.
Yes.
So that's a remote end. So that is one of the like I feel that's a mistake in like in this case.
Yeah.
But I don't know like why they have given. But in our modeling, we are going to energize this transformer. So this side circuit breaker, this transformer circuit breaker, we are going to study and we are going to implement something like that. The same thing they have done. Phase A closed stuck, then phase B opens at 300 milliseconds and phase C closed stuck, which is they are going to open, which is they are going to de-energize it.
Yes.
So you get the point, right? Like 99999, which is
Nothing
they are
happened.
not going to open it. They are not going to close it. 0.3 they are going to open. They are going to close it. And the circuit breaker C also the same thing. Like 999, it's not going to do anything. So they are trying to show some worst case here. Like that's why they have used a capacitor, because a ferroresonance will mainly occur the interaction between a capacitor
And
and the nonlinear inductance. So when I say network parameters, it's mainly I'm just talking about the capacitor.
yes.
So the interaction between the capacitor and the interaction between the a non-linear inductor, that is ferroresonance.
Yeah.
I'll try to just run this. Sorry, 1 minute. Fine. I'll try to just run this. I don't know. I've never run like I've never simulated this. We can just check what is ferroresonance and how that will happen. Yeah.
Yeah.
So yeah, this is ferroresonance, Manchu. Like the oscillations will be something like this.
Okay.
So so these are the some oscillations. So
Yeah.
like if you have oscillations something like this, then you can say that there is some ferroresonance. Here also they are trying to measure at the HV side and LV side.
Yes.
So always I'll recommend that always try to do HV side and LV side. Fine. Fine. Okay. So this is how a ferroresonance will look like. So the oscillations. So but in our case there is no oscillation, something like that, right?
Yes.
We don't had any oscillations.
What the guys are going to do with this then if there is a ferro resonance? What they are
Yeah,
how they
there
are
is
going
some
to control it?
mitigation technique. Yes.
Yes.
The first mitigation technique we can say that you have to closely look at the circuit breaker poles. Like you should not close the individual what to say the individual poles. Like if you
Okay.
want to close it, like you have to close it at the three at
All
both the
together.
time, like,
Okay.
all together. So that is one kind of basic mitigation technique you can give. The second one is you can increase some losses.
Yeah.
So you have to play with some losses so that you can mitigate the over voltage.
Okay.
So this is in per unit. So this is just went up to 3.5, I think so. So the second mitigation technique is you have to increase some losses.
Yeah.
So transformer loss, if you just increase that, then like you can just control the thing, like yeah, you can just control the the over voltage.
Yeah. Yeah.
And then yeah, so and then they used to go some filters, but I never worked on filters. I never used any filters, like I have no knowledge on that, but
Okay.
I've read it in some papers, like not an IEEE paper. I can't believe that, like I can I have read in some thesis.
Yeah.
If you have any IEEE paper stating
Even
that, if you
even IEEE paper you can't believe like every paper unless some paper is like signed for some like special standard or special like conference
yeah,
because
yeah, yeah,
yeah, because
yes.
nowadays the people just copy paste from somewhere and just publish something.
Yes, so I won't believe like other than IEEE papers. So that's my mentality. Like I've read it one of the paper. I can show you right now also. I don't know, I just closed. Yeah, this is the paper. This is this thesis. Here they have used some Butterworth filter, so filter. So some kind of filter. That is the mitigation technique they have proposed. But
Okay.
I don't know like how for what extent we can use this.
Okay.
But we can use the basic mitigation technique, which is we cannot use this, which is a single pole operation. Like altogether, if you close all these three, you may end up without a ferroresonance. So that is the basic main. Right? And then I have so there will be some. I have no experience on that, but I can give you some points on that. Sometimes people will have introduce some loads. Like
Yes.
generally, we have did with no load, right? So
Yeah.
I'll just show you the cases. Everything is at no load. Like see at no load.
Yes.
We have not introduced any load. Like at no load, we are going to do that. But sometimes people will introduce a load. Like this is a light load condition. Like no load or light load condition. Like
Yes.
30 MPa, 25, 0.25 megawatt is a light load. So if you fine, we can just check that. I'll 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 just increase this, say 5 megawatt. But I will not suggest this because I don't have experience on this. But for simulation purpose, we can just check it. We can just try to note down the value 0.8. So the over voltage not 0.8. It is not coming. Yeah. So the over voltage is 3.8, right? I have
Yes.
just increased the load, which act as a damping factor.
Yeah.
Which act as a damping factor. Like I'll try to just run this. I've read it in some papers, but I never used it. So in our projects.
Okay.
Okay. So this is mitigated, right? So we can't see
Yes.
anything on that.
Yes. Yes.
So it's good. Show marker and yeah, which is one per unit. Like you don't have like the plot is saying that you are not having any oscillations
Oscillations. Yes.
just by increasing some load. But this load should be like if you're going to increase some load, that should be a valid thing, because the transformer will not overload. Like many places away from India, transformers they will not load up to 50%, right?
Yeah.
The transformers they will not load up to 50%. So giving some load is always the tough part. So we don't generally give this. Like we don't generally use this as a
Okay.
mitigation technique. But in some papers I have read it, so I just want to give some points on that.
Okay. No problem.
Yeah, yeah. Any doubts on ferro resonance, Manchu?
No.
Yeah. So and then yeah, the points. Yeah, everything was explained. And okay, the documents I have to share is I'll share this document, the cases which we have done
Yes.
with 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 some modeling. Like I'll give you energizing model, and I'll give you a model with VT.
That would be great. Yes. At
Uh,
least I can keep that as a reference. To understand
mhm.
the thing. Yes.
Yeah, yeah, you can use it and try to just run it, and
I will. I will.
yeah, try to do it.
Yes. I will do.
So this is what I just want to explain on ferro resonance, like about ferro resonance, and yeah, any doubts on this, like on today's class, ferro
No.
resonance?
No. Not at all.
So tomorrow we'll be having class at 1:30.
Yes.
So we'll be talking about transient, like sorry,
TRV.
TRE, or if you want to discuss any other points, like we can discuss tomorrow also, not an issue.
Okay. Okay.
Yeah, so I'll share you the modeling with
Yeah.
that with this data you asked, right?
Yes.
This one. Yeah,
Yeah.
I'll
Yeah.
share it also.
Yes.
In our WhatsApp group itself, I will share you. Not an issue.
Okay. That would be great.
So
And I
you
will
can
send some GIS earthing specification and a couple of
yeah,
papers on.
yeah. Yes. So that would be great.
Yes.
Okay, Manchu, like we can meet tomorrow.
No problem, mate. Thank you so much.